Look up at the night sky on a clear, dark evening, and you might see a faint, fuzzy patch of light among the constellations. To the naked eye, it seems almost insignificant, a smudge of cosmic dust. But what if I told you that this tiny, blurry spot is actually one of the most incredible structures in our galaxy, a dense, spherical city of hundreds of thousands of ancient stars, all bound together by gravity in a cosmic dance that has lasted for billions of years. These are globular clusters, and they are far more than just beautiful collections of stars. They are time capsules, holding within them secrets from the earliest epochs of the universe, and some of their discoveries are so strange, they challenge the very foundations of modern astronomy. Imagine a place where stars are packed so tightly together that the night sky from a hypothetical planet within one would be ablaze with countless suns, creating a perpetual, brilliant daylight. This is the reality within a globular cluster, a relic from a time when the universe was young and galaxies were just beginning to form. For centuries, these clusters have captivated astronomers, but only recently have we begun to peel back the layers of their mysteries, uncovering findings that are as bewildering as they are profound. We're about to embark on a journey through 30 of the most peculiar and mind-bending discoveries about these ancient star cities, from stars that shouldn't exist to the potential hiding places of dark matter and rogue black holes. Each revelation pulls us deeper into a cosmic puzzle that redefines our understanding of stellar evolution, galactic history, and the very fabric of the cosmos. So prepare to have your perspective shifted, because what we're uncovering in these glittering islands of stars is stranger than anything we could have imagined. Our exploration of these celestial anomalies begins with a discovery so fundamentally unsettling it threatened to rewrite the very timeline of existence. Picture astronomers, armed with the most advanced instruments, carefully measuring the light from ancient stars within clusters like M92 and the intriguingly named Methuselah star, HD 140283. The data that came back was nothing short of revolutionary, pointing to ages of nearly 13.8 billion years. This number alone might not seem startling until you place it next to the most precise calculation for the age of our universe, which sits at approximately 13.77 billion years. The implication was staggering. Here were stars that appeared to be older than the cosmos that birthed them. It was a paradox that echoed through the halls of astrophysics departments worldwide, a direct challenge to our understanding of cosmic dawn. How could a structure exist before the event that created everything? The initial interpretation suggested our foundational clocks, the methods we use to date both the universe and stars, were catastrophically wrong. The models of stellar evolution, so carefully constructed, and the cosmological parameters from the Big Bang theory both seemed to be on trial. This age paradox forced a period of intense and critical re-examination. The resolution, as it turned out, wasn't in discarding our theories, but in refining them with incredible precision. For the universe's age, derived from the expansion rate and the afterglow of the Big Bang, known as the cosmic microwave background, scientists realized that tiny uncertainties in measurement could account for a margin of error of tens of millions of years. On the stellar side, determining a star's age is an intricate art. Astronomers rely on models that interpret a star's temperature, luminosity, and chemical composition. The breakthrough came with the understanding that the initial oxygen and iron content of these primordial stars drastically influences their aging process. A star born with slightly more oxygen, for instance, burns its fuel more slowly, causing it to appear younger than it truly is when measured with older models. By incorporating these subtle elemental nuances, the estimated ages of these ancient stars gracefully shifted to just under the universe's age, resolving the apparent contradiction. The true legacy of this discovery, however, wasn't just a corrected number. It was the profound humbling and subsequent strengthening of our cosmic science. It proved that our methods are resilient, capable of withstanding their own most bizarre predictions and emerging more robust. It taught us that the universe's oldest stars are not just ancient relics, but precise instruments in their own right, their very light holding the keys to calibrating the story of everything. Just as we resolved one cosmic puzzle, another, equally profound mystery emerges from the depths of our data. While we expected the ancient universe to be a bustling factory for these stellar cities, we're confronted with a startling shortfall. Large, majestic spiral galaxies like our own Milky Way should, according to our most sophisticated computer models of cosmic evolution, be surrounded by thousands of globular clusters. Yet when we count them, we find only a few hundred. The majority of these ancient assemblies are simply missing, presenting astronomers with a ghost population of clusters that should be there, but aren't. This enigma, known as the missing cluster problem, forces us to consider a more violent and dynamic galactic history than we had ever pictured. One leading theory points to the destructive power of the galaxy itself. As a globular cluster orbits through a galaxy's disk or plunges close to its dense central bulge, it experiences immense gravitational forces, cosmic tides. These repeated tidal shocks can literally pull the cluster apart, stripping away its outer stars over billions of years until the entire structure is dissipated, its stars scattered into the galaxy's halo. It's a slow-motion demolition on a cosmic scale. We may be seeing only the hardy survivors, the clusters with stable orbits that have miraculously avoided these galactic danger zones for eons. Another quiet but relentless process is evaporation. Within a cluster's densely packed core, stars are in constant motion, gravitationally interacting with one another. These intricate dances can fling the lower mass stars right out of the cluster, much like a slingshot. Over billions of years, this steady trickle of escaping stars causes the entire cluster to lose mass and weaken its own gravitational grip. For smaller clusters, this process can lead to their complete dissolution, fading from a brilliant city of stars into a diffuse, untraceable stream of individuals. This suggests that what we observe today could be just the tip of the iceberg, the most massive and resilient clusters that have withstood this relentless evaporation. But perhaps the most intriguing possibility is that the fault lies not in the destruction, but in the creation. Our understanding of the early universe is built on a foundation of powerful, yet incomplete, simulations. What if the conditions for forming a globular cluster were far more specific and rare than we've assumed? Maybe the primordial gas clouds that collapsed to form these clusters needed a perfect cocktail of density, temperature, and dark matter to trigger their formation, a recipe that was not as common as our models suggest. Alternatively, perhaps many infant clusters were born but were immediately stunted, their gas, the raw material for new stars, blown away by intense radiation from the first brilliant, short-lived supernova, or by powerful outflows from supermassive black holes in the earliest galaxies. This would have left them stillborn, unable to form the dense, populous star systems that could survive to the present day. The missing clusters are not just an accounting error. They are a ghostly fingerprint of the universe's most tumultuous and formative era. Their absence tells a story of survival, destruction, and perhaps of a cosmic infancy that was even more chaotic and extreme than we have yet dared to imagine. Just when we thought we had a handle on their history, globular clusters revealed another layer of their complexity, one that shattered a long-held astronomical belief. For decades, the textbook description was simple and elegant. A globular cluster was a single, simple stellar population. Picture a vast, spherical swarm of stars, all born from the same primordial cloud of gas at the same exact time, all sharing the same chemical recipe. They were cosmic fossils, frozen in time and perfect for studying the conditions of the early universe. This clean, one-generation model was the bedrock of our understanding for nearly half a century. But then, with the power of advanced telescopes like the Hubble Space Telescope and sophisticated spectroscopic analysis, astronomers began to look closer, and the simple picture completely fell apart. The data told a story that was not simple at all. The light from these stars revealed distinct chemical signatures, proving that within a single cluster, there were not one, but multiple generations of stars. And the differences weren't subtle. They were profound, pointing to a dramatic and turbulent early life for these cosmic cities. The key evidence lies in the abundance of specific light elements. The first generation of stars in a cluster, the true pioneers, show a chemical fingerprint that matches the pristine gas of the early universe, rich in hydrogen and helium, but with very low amounts of heavier elements forged in stellar cores. Yet, a significant portion of a cluster's stars, a second, and sometimes even a third generation, show a completely different signature. They are enriched with extra helium, nitrogen, and sodium, while paradoxically showing a depletion of other elements like carbon and oxygen. This is the telltale sign of stellar nucleosynthesis, the process where stars themselves forge new elements. But for these new elements to be incorporated into a new generation of stars, they had to come from somewhere and be injected back into the cluster's reservoir of gas. This leads to one of the most compelling mysteries in modern astrophysics. What was the source of this pollution? The prime suspects are the most massive stars from that first generation. The fastest living of these stars, known as asymptotic giant branch stars, are thought to be prolific producers of helium and nitrogen, expelling these newly forged elements through powerful stellar winds in their final stages of life. Alternatively, some theories point to massive, rapidly rotating stars that shed their enriched outer layers, effectively seeding the surrounding gas with their unique chemical byproducts. This polluted gas, now laced with helium and nitrogen, would then collapse under gravity to form the next wave of stars, each one chemically distinct from its parents. This discovery of multiple populations forces a radical rethinking of how these clusters formed and evolved. The old model of a single, quick collapse was no longer viable. Instead, we must envision a far more dynamic and protracted birth. A globular cluster's early history was likely a dramatic cycle of star formation, death, and rebirth, all compressed into a relatively short cosmic timeframe. The first generation of massive stars would have lived fast and died young, exploding as supernovae or shedding their outer layers, their violent deaths enriching the limited supply of gas still lingering within the cluster's gravitational grip. This newly polluted gas then triggered a second wave of star formation, creating the chemically distinct generation we see today. But this process presents a colossal problem known as the mass budget problem. The amount of enriched gas we see locked in the second generation of stars is enormous, often making up more than half the cluster's stellar mass. The first generation of massive stars simply doesn't seem numerous or powerful enough to have produced all this extra material. Where did it all come from? This is the crux of the mystery, and it suggests that our understanding of the first stars themselves, or perhaps the involvement of other exotic objects, is still critically incomplete. The presence of multiple stellar populations transforms our view of globular clusters from quiet, frozen relics into the vibrant, complex archaeological sites they truly are. They are not static monuments, but dynamic stellar systems that lived through intense, self-driven periods of change, their very stars recording a history of creation, destruction, and rebirth written in the language of elemental chemistry. Yet, even the complex story of multiple generations cannot account for one of the most visually striking anomalies found within these ancient star clusters. In a population of ancient, cool, red stars, astronomers began to spot stars that simply did not belong, stars that were burning fiercely with a hot, blue light, appearing billions of years younger and more massive than any of their neighbors. Dubbed blue stragglers because they seem to lag behind the normal evolutionary path, these stars are the ultimate cosmic rule breakers. They are massive, luminous, and energetic stars living in cities where all the fuel for creating such behemoths should have been exhausted eons ago. Their very existence in such an old environment is a direct affront to our understanding of stellar life cycles, forcing us to consider that in the crowded downtown of a globular cluster, stars have found a way to cheat death and reclaim their youth. The leading explanation for this stellar rejuvenation hinges on the extraordinary density of these environments. In the core of a typical globular cluster, stars are packed together so tightly that the space between them is vastly smaller than in our own galactic neighborhood. This creates a celestial traffic jam where close encounters and even direct collisions are not just possible, but inevitable over billions of years. Imagine two aging, sun-like stars on a gravitational dance that goes terribly wrong, resulting in a head-on collision. The resulting cosmic pileup would merge their hydrogen fuel into a single, new, more massive and hotter star. This newly formed blue straggler would instantly appear younger and bluer than its peers, a phoenix born from the wreckage of its predecessors. This violent formation method is thought to be the dominant process in the very densest cluster cores, where stellar traffic is at its worst. However, a second, more subtle, and perhaps even more common process is at work in the slightly less crowded regions of a cluster. A vast number of stars in the universe are born in binary systems, two stars locked in a mutual gravitational embrace. In such a pair, if one star begins to age and swell into a red giant, its outer atmosphere can be gravitationally stripped away by its closer, denser companion star. This process, known as mass transfer, essentially funnels fresh hydrogen fuel onto the smaller star. The recipient star, now bulking up on this new material, becomes more massive, heats up, and reignites its fusion processes with a new intensity. It's a stellar makeover, turning an old star back into a blue, youthful-looking one. In some cases, the two stars can even spiral inward and merge completely, creating a single, rejuvenated star that is virtually indistinguishable from one formed by a direct collision. This binary channel provides a continuous, quiet mechanism for producing blue stragglers without requiring a spectacular, high-speed crash. The presence of blue stragglers, therefore, is more than just a curiosity. It is a direct window into the dynamic and interactive lives of stars in these dense environments. By studying their locations, whether they are concentrated in the chaotic core or scattered throughout the cluster, astronomers can map the internal dynamics and history of the cluster itself. They serve as living proof that a globular cluster is not a sterile museum of ancient stars, but a vibrant, evolving ecosystem where stars can interact, merge, and fundamentally alter their destinies. These brilliant blue anomalies are the ultimate testament to the idea that even in the oldest places in the universe, there are still ways to start life anew. This concept of a dense, dynamic environment where stars are constantly interacting and colliding to form new objects leads us directly to one of the most thrilling and unexpected discoveries in modern astronomy: the confirmed presence of black holes lurking within these ancient star cities. For the longest time, the conventional wisdom was straightforward. Globular clusters should be clean of stellar mass black holes. The reasoning was rooted in the very same dynamical processes that create blue stragglers. In a crowded cluster core, black holes, being the most massive objects there, would engage in a relentless gravitational dance with their stellar neighbors. Through a process called dynamical friction, these heavy black holes would sink to the very center of the cluster. Once there, complex multi-body interactions would act like a cosmic slingshot, efficiently ejecting the vast majority of them entirely out of the cluster and into the galactic halo. It was a tidy theory, suggesting that any black holes formed in the cluster's youth would have been evicted billions of years ago, leaving behind a quieter stellar population. This long-held belief was completely overturned by two powerful lines of evidence. The first came from the revolutionary field of gravitational wave astronomy. When observatories like LIGO and Virgo began detecting ripples in spacetime from colossal black hole mergers across the universe, astronomers immediately started searching for the most likely breeding grounds for these events. The dense, interaction-rich environment of a globular cluster emerged as a perfect candidate. Within such a crowded stellar metropolis, black holes that managed to avoid ejection could find each other. They could form binary pairs through gravitational capture, and then, over time, their orbits would tighten through further dynamical encounters until they finally spiraled inward and merged in a spectacular release of energy that we can detect from Earth. The very signals picked up by LIGO strongly suggested that globular clusters weren't just passive hosts. They were active factories for creating these cosmic collisions. The second, more direct line of evidence came from painstaking observations of the clusters themselves. By meticulously tracking the motions of individual stars and clusters, like NGC 3210, astronomers noticed something peculiar. Certain stars were being subtly tugged, their paths influenced by an unseen, massive companion. The only explanation for the magnitude of these gravitational perturbations was the presence of an invisible object with a mass several times that of our Sun, a stellar mass black hole in a binary system. In other clusters, researchers have even detected the faint X-ray glow of accretion, where a black hole is actively pulling material away from a companion star, creating a telltale signature of its dark presence. These observations confirmed that not only do black holes persist in these environments, but they are also integrally involved in the cluster's ongoing dynamics. So, how do these cosmic predators avoid being kicked out? The answer seems to lie in the very complexity we failed to initially appreciate. Instead of a simple process where each black hole is individually ejected, modern simulations show that a rich and complex social structure emerges among the black hole population. A large group of them can form a stable, massive core in the cluster's center, effectively hiding in plain sight. Within this central black hole subsystem, they interact with each other, forming and breaking binary pairs. It's often through these intricate dances that the lightest black holes in the group get ejected, acting as a gravitational release valve that helps the heavier, more dominant black holes remain bound to the cluster. This changes our entire perspective on the life cycle of a globular cluster. They are not just collections of stars, but complex ecosystems with a hidden hierarchy where an invisible population of black holes can dictate the core's stability and even influence the distribution of the visible stars around them. These findings transform our understanding of these ancient structures from simple stellar relics into dynamic engines capable of producing some of the most violent and energetic events in the universe. Just when the dynamic interactions within clusters seemed complex enough, astronomers stumbled upon a puzzle so persistent it has earned its own name, the Great Second Parameter Problem. It's a mystery that lies in the very heart of how stars live out their final years. To understand it, we first need to look at the horizontal branch, a specific phase in the life of a star that has exhausted the hydrogen fuel in its core. Picture a stable, long-lasting phase where stars fuse helium in their cores, and on a standard graph of stellar properties known as the Hertzsprung-Russell diagram, these stars line up along a nearly horizontal line, hence the name. For a long time, astronomers noticed a clear and predictable pattern. The primary factor determining how a star appears on this horizontal branch is its metallicity, which is the abundance of elements heavier than hydrogen and helium. A cluster with high metallicity will have a horizontal branch packed with redder, cooler stars. A cluster with low metallicity, typical of ancient globular clusters, will have a horizontal branch dominated by hotter, bluer stars. This made perfect sense and was a cornerstone of stellar evolution theory. But then, observers began comparing different globular clusters and found something that broke this elegant rule. They found two clusters with virtually identical metallicities, born from what seemed like the same primordial recipe, yet their horizontal branches looked nothing alike. One might be dominated by a long, blue tail of hot stars, while the other would appear stubby and red. Since metallicity, the first parameter, was the same, something else had to be responsible for this dramatic difference. This unknown factor became known as the second parameter, and identifying it has become a grand challenge in astronomy, a decades-old quest that continues to this day. The hunt for this second parameter has led scientists down many fascinating paths, with each candidate offering a compelling but incomplete explanation. One of the most straightforward suspects is age. Perhaps the cluster with the bluer horizontal branch is just a little bit younger. A younger star of the same mass and composition will have a hotter, more helium-rich core when it reaches the horizontal branch phase, potentially leading to a bluer appearance. While age differences do seem to explain some of the variation, particularly between clusters in our galaxy's inner and outer halo, they fail as a universal solution. Astronomers have found pairs of clusters with the exact same age and metallicity that still display starkly different horizontal branches, proving that age alone cannot be the elusive second parameter. This leads to another powerful contender, helium abundance. We already saw how multiple stellar populations within a cluster can create stars with enhanced helium. Imagine a star born from gas polluted by the winds of earlier generations, giving it a higher initial helium content. Helium is heavier than hydrogen, so a helium-rich star has a denser, more compact core from birth. When it evolves onto the horizontal branch, this compact core makes the star burn hotter and bluer. A cluster with a significant second generation of helium-rich stars would therefore have a much bluer horizontal branch than a cluster of the same metallicity, but with only a first generation. This is a very strong candidate, as it directly links the multiple population phenomenon to this long-standing puzzle. Yet even here, there are complications. Precise measurements of helium abundance are incredibly difficult to make, and in some cluster pairs, the helium explanation doesn't seem to fully account for the observed differences in stellar distribution. Other proposals venture into even more complex territory. Some researchers suggest the total mass of the cluster itself could be the second parameter. A more massive cluster has a stronger gravitational pull, which might influence the rate of stellar interactions and collisions in its past. Perhaps these dynamical effects, by creating merged stars or altering binary systems, have changed the masses of the stars now arriving on the horizontal branch, thereby shifting its color. Another intriguing idea points to the rotation of stars. If stars in one cluster rotate faster on average than those in another, this can affect their internal mixing and structure, altering their evolutionary path and ultimately their position on the horizontal branch. The challenge is that these factors are deeply intertwined, making it nearly impossible to isolate a single, definitive cause. The enduring nature of the second parameter problem is a profound reminder of the complexity of stellar physics. It shows us that the simple one-factor-fits-all models of the past are insufficient to describe the rich diversity of the cosmos. The solution may not be one single parameter, but a combination of several age, helium, dynamics, and rotation all playing a role to different degrees in different clusters. This ongoing puzzle forces astronomers to continually refine their models and deepen their observations, acknowledging that even in the predictable twilight years of a star's life, there are still layers of mystery waiting to be unraveled. While we grapple with the complex internal lives of globular clusters, our galaxy is simultaneously orchestrating a grand, slow-motion act of cosmic demolition on their outermost borders. This brings us to a breathtaking discovery made possible by wide-field sky surveys, the revelation that many of these ancient clusters are not the perfect, isolated spheres they appear to be. Instead, they are slowly being unraveled, their stars being gently peeled away by our Milky Way's immense gravitational pull, forming vast, ghostly rivers of stars that stretch for thousands of light years across the galactic halo. These are tidal tails and stellar streams, and they represent the final, dramatic chapter in the life of a globular cluster as it is consumed by its host galaxy. To understand how these structures form, picture a globular cluster orbiting the Milky Way. It's not a simple, circular path. It's an elongated ellipse that periodically brings the cluster close to the galaxy's dense central bulge, and then swings it far out into the sparse halo. Each time the cluster makes a close pass to the galactic center, it experiences a profound gravitational phenomenon known as a tidal force. Think of it this way: the side of the cluster closest to the galaxy feels a much stronger gravitational tug than the side farther away. This difference in pull, the tidal force, acts to stretch the cluster, much like the Moon's gravity stretches Earth's oceans to create tides. Over billions of years and countless orbits, this relentless stretching does more than just deform the cluster's shape. It provides the extra gravitational nudge needed to overcome the cluster's own gravity for the stars orbiting at its outermost edge. These stars, once loosely bound, are now liberated, streaming away from the cluster in two opposing directions, one leading the cluster in its orbit and one trailing behind. The result is a long, thin, and incredibly faint ribbon of stars, a tidal tail that traces the cluster's orbital path through space. The poster child for this magnificent process is the cluster Palomar 5. Through dedicated observations, astronomers have uncovered that Palomar 5 is actually the compact, dense heart of a structure that spans over 20 degrees across the sky, a stream of stars that is itself many times more massive than the cluster that remains. The cluster we see today is merely the surviving core, while the spectacular tails represent the majority of its original stellar population, now stripped away and lost to the galaxy. This finding is transformative. It suggests that what we classify as a faint, diffuse globular cluster today may, in fact, be the final, dying ember of a once much larger and more massive object, currently in the throes of being completely dissolved. Palomar 5 is not unique. We've observed similar, though often fainter, streams around other clusters like NGC 5466, indicating that this process is a common fate for many of these ancient systems. But the scientific value of these stellar streams extends far beyond simply documenting the death of clusters. They have emerged as one of the most powerful tools we have for mapping the invisible skeleton of our galaxy, its dark matter halo. A stream of stars, once freed from its cluster, behaves like a cosmic probe. Its stars, all moving together in a coherent, predictable path, are sensitive to any slight variations in the galaxy's gravitational field. If the Milky Way's gravity were perfectly smooth and symmetric, these streams would form long, perfectly thin and linear filaments. However, that's not what we see. Observations reveal that many streams are not straight lines. They exhibit kinks, gaps, and bends. These imperfections are the forensic evidence of past gravitational disturbances. A passing clump of dark matter, a close encounter with a dwarf galaxy, that has since been consumed, or even the gravitational wake of a massive object like the Milky Way's central bar, can all leave a distinct scar on the structure of a stream. By meticulously modeling the exact shape and density of a stream like that from Palomar 5, astronomers can work backwards, essentially using the stream as a gravitational seismograph to detect and measure the mass and location of the invisible perturbers that have affected it. This allows us to chart the distribution of dark matter in a way that was previously impossible, turning these beautiful, ephemeral structures into precision instruments for probing the deepest secrets of our galactic home. And so we arrive at a discovery that takes the idea of multiple stellar populations and pushes it to a truly baffling extreme, one that manifests as a strange overabundance of what astronomers call polluted stars. This isn't pollution in the earthly sense of smog or debris, but rather a celestial contamination, a distinctive chemical fingerprint imprinted on a star at its birth. Within many globular clusters, a staggering number of stars, sometimes the overwhelming majority, display this anomalous signature. They are bizarrely rich in specific elements like nitrogen and sodium, while simultaneously being depleted in others, most notably carbon and oxygen. This pattern isn't just a minor curiosity, it's a screaming anomaly. In the nuclear furnaces of normal stars, the processes that create nitrogen and sodium are directly linked to the destruction of carbon and oxygen. To find this signature so widespread means we are witnessing the fossilized evidence of a profound and pervasive chemical event that permanently altered the raw material from which these stars were forged. The hunt for the source of this celestial pollution leads us directly to the dramatic lives and deaths of the very first stars to ignite in the cluster. The leading suspects are two distinct types of stellar veterans from that primordial generation. First, consider the asymptotic giant branch stars, or AGB stars for short. These are aging, bloated giants in their final, unstable stages of life. Deep within their layered interiors, a process known as hot bottom burning occurs, where the intense heat at the base of the star's convective envelope acts as a nuclear processing plant. Here, carbon is readily fused into nitrogen. At the same time, in a slightly deeper layer, protons can be added to neon nuclei to create sodium. These newly forged elements are then dredged up to the surface by powerful convection currents and finally expelled into the surrounding space through relentless, dusty stellar winds. It's a slow but prolific method of seeding the cluster's gas with a very specific chemical cocktail, one rich in nitrogen and sodium, but poor in carbon and oxygen. The second prime suspect is a class of massive, rapidly rotating stars that lived fast and died young. In the early universe, it's thought that some stars were born spinning at incredible speeds. This rapid rotation creates immense centrifugal forces that stir the star's interior like a blender, mixing the nuclear ashes from the core throughout its vast volume. This mixing brings hydrogen from the outer layers down into the hot regions, where carbon and oxygen are being destroyed to produce nitrogen. Concurrently, the high temperatures enable the proton capture reactions that create sodium. Because these stars are so massive, their powerful radiation pressure can then easily blow their enriched, mixed outer layers away in an intense stellar wind long before they ever go supernova. This provides a mechanism to release this uniquely polluted material quickly and efficiently into the cluster environment. But here's where the mystery deepens into what's known as the mass budget problem. For the pollution scenario to work, the first generation of polluter stars had to produce enough enriched material to form the entire second generation we see today, which often makes up more than half the cluster's current stellar mass. When astronomers run the numbers, they hit a wall. The predicted number of AGB stars, or fast rotators, from the first generation simply doesn't seem sufficient to have polluted such a vast reservoir of gas. It's as if a single chef was tasked with preparing a meal for 1,000 people, but only had enough ingredients for 100. This glaring discrepancy suggests that either our understanding of these polluting stars is fundamentally flawed. Perhaps they were even more massive or efficient than our current models allow, or that we are missing a key contributor to this process entirely. Some theorists have even proposed more exotic sources, like supermassive stars that have never been observed, to account for the sheer volume of polluted material. This mass budget problem remains one of the most active and contentious areas of research in globular cluster science, a clear sign that our models of stellar evolution, even for these ancient stars, are still a work in progress. This relentless churn of stellar interactions and mergers points toward a fundamental organizing principle at work within these clusters, a slow but unstoppable process that sorts the entire population by weight. Imagine taking a container filled with a mixture of sand, pebbles, and heavy rocks and shaking it vigorously for billions of years. What happens? The larger, denser rocks will gradually settle toward the bottom, while the finer sand rises to the top. This is a perfect analogy for a phenomenon known as mass segregation, and it's a dominant force shaping the internal structure of every globular cluster. The mechanism driving this cosmic sorting is something called dynamical friction. In the empty void of intergalactic space, an object's mass doesn't affect its trajectory. A pebble and a planet would follow the same path if set moving at the same speed. But within the crowded, gravitationally rich environment of a star cluster, everything changes. As a more massive star, let's say a heavy stellar remnant like a neutron star or a black hole, moves through a sea of lighter stars, its immense gravity creates a slight wake, a local overdensity of stars behind it as it travels. This gravitational wake exerts a subtle but persistent drag on the massive object, slowly sapping its kinetic energy and causing it to lose speed. It's like moving through a dense crowd. A single person can slip through easily, but a large group creates a commotion that slows it down. This loss of energy causes the heavy object's orbit to decay, forcing it to spiral inexorably inward toward the cluster's center of gravity. Over hundreds of millions of years, this process efficiently funnels the most massive residents of the cluster into the core, while the lighter, lower mass stars are gravitationally pushed out to the outskirts. The result is a starkly segregated city where the downtown core is packed with heavyweights, and the suburban halo is composed of the lighter stellar population. The implications of this segregation are profound, transforming the cluster's core into an entirely different environment from its outer regions. This central zone becomes a stellar demolition derby, a place of extreme density where close encounters are the norm rather than the exception. With so many massive objects, black holes, neutron stars, and giant stars crammed into such a small volume, the gravitational interactions are constant and fierce. This dramatically increases the probability of spectacular events. Binary star systems, which are common throughout the cluster, can have their orbits violently perturbed when a third massive object passes too close. These interactions can tighten the binary's orbit, sometimes to the point where the two stars merge in a cataclysm that could produce a blue straggler or even a supernova. In other cases, the interloper can break the binary apart, stealing one star and flinging the other away at high speed. This core is also the most likely birthplace for the binary black hole systems that LIGO detects. Two solitary black holes, having sunk to the center, can find each other and become gravitationally bound through a complex dance with other stars. Their subsequent merger sends ripples through the fabric of spacetime itself. The core is not just a dense collection of stars. It's a dynamic engine for creating the most exotic and energetic phenomena in the cluster. Furthermore, This concentration of mass in the core has a controlling influence on the entire cluster's long-term evolution and ultimate fate. The dense central knot of heavy objects acts as a gravitational anchor, helping to stabilize the cluster against the tidal forces of the galaxy. A cluster with a well-segregated, massive core can potentially survive for much longer than one that has been stripped of its heavy inhabitants. However, this same core can also be the source of the cluster's destruction. The intense gravitational interactions in the core can act as a factory for producing high-velocity stars. When a lightweight star has a close encounter with a tight binary system of heavy objects, it can be slingshot out of the core at tremendous speed, sometimes even escaping the cluster entirely. This process, over billions of years, steadily evaporates the cluster from the inside out. In the most extreme cases, the black holes in the core can themselves interact, with the lighter ones being ejected into the galactic halo. This ongoing loss of mass, both in stars and in the black holes that help bind the core, gradually weakens the cluster's gravitational glue, making it more susceptible to being torn apart by the Milky Way's tides. Mass segregation, therefore, is not a static state, but a dynamic process that writes the life story of a globular cluster, from its mature, organized structure to its eventual dissolution, all dictated by the silent, relentless sinking of its most massive citizens. But just as we've painted a picture of globular clusters as exclusively ancient relics, the universe presents us with a fascinating exception that forces us to expand our definition. Scattered throughout nearby galaxies, and even within our own Milky Way, astronomers have found massive, dense star clusters that defy the classic age rule. They are the young globulars. These are not the 13-billion-year-old fossils we've come to know, but vibrant, brilliant stellar nurseries that are mere infants in cosmic terms, some only a few million years old. Their existence is a monumental discovery because it proves that the process of building these immense stellar cities did not end in the early universe. It has been ongoing, offering us a rare and precious window into the violent birth processes that shaped their ancient counterparts. One of the most spectacular places to find these young clusters is in our neighboring galaxy, the Large Magellanic Cloud. There, we find objects like R136, a stellar behemoth located in the Tarantula Nebula. R136 is not just a cluster, it's a cosmic fireworks display in its opening act. It's home to some of the most massive and luminous stars ever recorded, true stellar monsters that are burning through their fuel reserves at a breathtaking rate. The intense radiation and powerful stellar winds from these giants are actively sculpting the surrounding nebula, blowing vast bubbles and creating intricate structures of gas and dust. This is a snapshot of what the environment around a newborn globular cluster must have looked like billions of years ago, a chaotic, energetic, and intensely productive cauldron of star formation. By studying R136, we can observe firsthand the feedback processes where massive stars influence their own birth environment, potentially shutting down further star formation or, conversely, triggering new waves of it in nearby gas clouds. This dynamic is crucial for understanding the mass budget problem in ancient clusters. We can see how much gas is expelled and how quickly, giving us real-time data on the efficiency of converting raw material into stars. Even within our own galactic backyard, we have stunning examples of this phenomenon. Consider the Arches cluster, located a mere 25,000 light-years from Earth, right in the tumultuous region near our galaxy's center. This cluster is incredibly young, at only around 2 to 2.5 million years old. To put that in perspective, while the ancient globular clusters were already older than Earth is today, the light from the first Homo habilis was just beginning its journey to Earth when the Arches cluster ignited. It is a spectacularly dense collection of stars, rivaling the core density of the oldest globulars, but it is blazing with the hot, blue light of youthful, massive stars. Its location is key. It sits deep within the central molecular zone of the Milky Way, an area flooded with dense gas and subjected to powerful tidal forces. This environment provides the perfect, albeit extreme, conditions for the rapid assembly of a massive cluster. Studying the Arches cluster allows us to investigate a critical question: can such a young, dense object survive its infancy? The forces at play near the galactic center are immense, and the cluster faces a constant battle against tidal stripping and the internal pressure from its own massive stars going supernova. Watching its evolution helps us understand the survival rate of these young clusters and how many of them might potentially live on to become the ancient globulars of the far future. The existence of these young massive clusters fundamentally changes our perspective on cluster formation. For a long time, the prevailing view was that the epoch of globular cluster formation was a unique period in the early universe, a special time when conditions were just right for their creation. The discovery of these relatively recent formations tells us that the recipe for building a dense, massive star cluster is not a lost art of the cosmos. It can still occur wherever there are sufficiently massive and dense clouds of molecular gas. The primary difference between the ancient globulars and these young counterparts often boils down to their environment and their chemical makeup. Young clusters like the Arches or those in the Large Magellanic Cloud tend to have higher metallicity, meaning they contain a greater abundance of elements heavier than hydrogen and helium, a signature of being formed from gas that was already enriched by many generations of earlier stars. This provides a fantastic opportunity to study how metallicity influences the initial structure and early evolution of a cluster, something we can only infer for the ancient metal-poor ones. These young globulars are, in effect, living laboratories. We can't rewind time to watch M13 form, but we can look at the Arches cluster and see the processes of mass segregation, stellar winds, and supernova feedback unfolding in real time. They are the missing link, bridging our understanding between the frantic, gas-dominated nurseries of the early universe and the serene, ancient stellar cities we see today, proving that the universe's capacity for creating grand structures remains as powerful now as it was billions of years ago. Now let's turn to a strange and brilliant class of stars that exist at the very edge of what we thought was possible, stars so extreme they push our models of stellar old age into uncharted territory. In some globular clusters, astronomers noticed an unexpected and intense source of ultraviolet light, a signature of incredibly hot objects. When they tracked down the source, they found something even more surprising: a peculiar group of stars located at the very tip of the horizontal branch, beyond the familiar blue stars. These are the blue hook stars, and they are the ultimate outliers, burning at temperatures so high they defy standard predictions for how a star should behave in its later years. A normal horizontal branch star is a stable, helium-burning object that has settled into a long, predictable phase of life. But blue hook stars are different. They appear to be even hotter, bluer, and more luminous than their neighbors, as if they've taken a sudden, dramatic turn off the main evolutionary path. Their presence creates a distinct hook at the end of the horizontal branch on stellar diagrams, a feature that signals something truly unusual is happening in their cores. One of the leading explanations for these extreme objects involves a stellar event of catastrophic intensity, known as a late helium flash. To understand this, picture a star leaving the red giant branch. It has exhausted the helium in its core, which has now contracted into a dense ball of carbon and oxygen, surrounded by a shell where helium is still fusing. In a typical star, this shell ignites the helium in a controlled flash, and the star moves onto the horizontal branch. But for some stars, the story doesn't end there. If the star loses an unusually large amount of its outer hydrogen envelope just before the flash, perhaps through powerful stellar winds or interactions in a binary system, the ensuing helium flash can be far more violent. It doesn't just ignite gently, it becomes a deep, convective upheaval that rips through the star's interior. This late hot flash doesn't occur in the core, but in the shell around it, and its violence is so great that it forces the star's entire outer envelope to expand dramatically and then rapidly contract again. The result is a star that is stripped down and reheated to an extreme degree, effectively rebooting its evolution and launching it into the blue hook region, far hotter and bluer than any standard horizontal branch star. Another compelling theory suggests the cause lies in a process called deep mixing. In this scenario, a star on the horizontal branch doesn't experience a single violent flash, but rather a continuous and profound internal churning. As the star burns helium in its core, the byproducts of that fusion, carbon and oxygen, begin to accumulate. Normally, these heavier elements would remain locked in the core. However, if the star rotates rapidly or has a particular internal structure that allows for exceptionally deep convection currents, these carbon and oxygen atoms can be dredged up from the core and mixed throughout the star's outer layers. This might sound like a minor detail, but it has a transformative effect. The sudden presence of carbon and oxygen in the star's atmosphere dramatically increases its opacity to certain wavelengths of light. In response, the star compensates by expanding its outer layers, but paradoxically, its core continues to heat up. This complex interplay between mixing, opacity, and energy transport can force the star to evolve along a unique track in the Hertzsprung-Russell diagram, pushing it into the blue hook territory. It's a slow burn transformation rather than a sudden explosion, demonstrating that even in a stable phase, a star's internal dynamics can lead to unexpected outcomes. We also cannot ignore the ever-present influence of binary companions. In the dense core of a globular cluster, a star on the horizontal branch might have a close partner. If the two stars interact, the hydrogen-rich envelope of the horizontal branch star could be stripped away by its companion through mass transfer. This removal of the outer layers would instantly expose the star's hotter, helium-burning interior, causing it to appear much bluer and hotter than it should, essentially creating a blue hook star through stellar cannibalism. Alternatively, the merger of two lower mass stars, such as two helium white dwarfs, could instantly create a single, more massive helium-burning star that ignites at a position on the diagram corresponding exactly to the blue hook. This channel provides a way to produce these extreme stars without requiring a late flash or deep mixing, highlighting once again how the crowded environment of a cluster can forge objects that would be impossible in isolation. The existence of blue hook stars is more than just a curious footnote. It is a direct challenge to the completeness of our stellar evolution models. These stars exist in a parameter space that was, until their discovery, largely theoretical. Their very presence forces astrophysicists to incorporate new physics into their simulations physics related to extreme mass loss, rotational mixing, and the precise nuclear reaction rates in helium-burning shells. By studying the exact distribution and properties of blue hook stars in different clusters, astronomers can calibrate these complex models. They serve as natural laboratories for testing the most extreme conditions a low-mass star can endure in its final chapters. Their brilliant, ultraviolet light is a beacon pointing toward the gaps in our understanding, reminding us that even for the most well-studied phases of stellar life, the universe still has a few surprises left in store. Moving from the internal dynamics of individual stars to the very systems that might orbit them, we arrive at a discovery that many once thought impossible: the existence of planets in the chaotic heart of a globular cluster. If the environment is hostile for stars, It is apocalyptic for planets. Picture the conditions: a sky perpetually filled with hundreds of stars as bright as Venus, all crammed into a space where the nearest stellar neighbor could be 100 times closer than our Sun is to Proxima Centauri. In such a gravitational maelstrom, the serene, stable conditions we associate with planet formation in our own galactic suburb seem like a distant fantasy. The delicate process of dust grains coalescing into planetesimals and then into full-fledged worlds would be constantly disrupted by the gravitational tug of passing stars, likely scattering the raw material or hurling infant planets into the abyss before they could fully form. For any world that did manage to coalesce, its long-term survival would be a constant gamble. A single close encounter with another star could easily fling it out of its orbit, either ejecting it from the cluster entirely or sending it careening into its parent star. The very concept of a stable, habitable zone where liquid water could persist for billions of years seems laughable in an environment where the stellar neighborhood is constantly being reshuffled. Yet, against all odds, we have found one. The first and most famous example is a planet orbiting a pulsar in the globular cluster Messier 4. This wasn't just the first planet discovered in a cluster. It was one of the very first exoplanets ever detected, period. The world itself is truly otherworldly. It orbits a pulsar, the super-dense, rapidly spinning corpse of a massive star that went supernova. The pulsar, known as PSRB 1257+12, emits beams of radiation as it spins, and by meticulously timing the slight variations in these pulses, astronomers inferred the gravitational pull of not one, but 3 orbiting bodies, one a planet with about 4 times the mass of Earth. The very nature of its parent star tells a violent story. The planet must have formed after the cataclysmic supernova explosion that created the pulsar, meaning it wasn't a survivor of the blast, but a phoenix born from the ashes. The leading theory suggests that the supernova event likely occurred in a binary star system. The explosion would have stripped mass from the companion star, and this material, falling onto the pulsar, could have formed a debris disk around it, a disk from which a new generation of planets could coalesce. This is a testament to the sheer resilience of planet formation. Even in the aftermath of a stellar catastrophe, the fundamental processes of accretion can still create new worlds. The extreme rarity of these detections, however, speaks volumes. Despite searching through many clusters, we have not found a single planet orbiting a main sequence, Sun-like star within one. This stark absence powerfully confirms our theories about the hostile environment. While the pulsar planet proves that planet formation can happen, its unique birthplace highlights just how difficult it must be for more conventional systems to survive. For a planet like Earth, orbiting a stable, long-lived star, the primary threat isn't the death of its star, but the relentless gravitational perturbations from outside. A close stellar flyby, occurring every few hundred million years, could be enough to destabilize an entire solar system, either ejecting planets, sending them into wildly eccentric orbits, or swapping them between stars. The fact that we see so few planets in clusters suggests that for every one that somehow endures, countless others have been destroyed or evicted over the cluster's long history. This makes the pulsar planet in M4 not just a curiosity, but a cosmic champion, a world that has weathered the most turbulent environment imaginable and serves as a profound reminder that the drive to form planets is a fundamental force of nature, persisting even in the most unlikely and unforgiving corners of the galaxy. This chemical detective story takes us even deeper into the heart of the multiple populations mystery, to a set of specific and peculiar relationships between elements that act like a cosmic fingerprint. The most telling clues aren't found in the presence of a single element, but in the stark, opposing patterns between them. Astronomers have uncovered what are known as anti-correlations. In a typical, pristine star, you would expect to see certain elements coexist in predictable amounts, but within globular clusters, we find stars with a strange and consistent imbalance. As the amount of sodium in a star increases, the amount of oxygen dramatically decreases. Similarly, in some of the most massive clusters, we see another pair locked in this celestial tug of war. Magnesium levels drop as aluminum levels rise. These are not random fluctuations. They are a precise, predictable signature that points directly to the nuclear fires where these elements were forged. To understand why this pattern is so significant, we need to step into the heart of a star. The process responsible is a specific type of nuclear fusion called high-temperature hydrogen burning, which occurs in a shell around the star's core. At these immense temperatures and pressures, a chain of nuclear reactions known as the neon-sodium cycle and the magnesium-aluminum cycle takes place. In the neon-sodium cycle, nuclei of neon, which is relatively abundant, begin capturing protons. This transforms neon into radioactive sodium, which then decays into stable sodium. The key point is that this process consumes oxygen along the way, as oxygen is a necessary component to create the initial neon. So, for every atom of sodium created, an atom of oxygen is effectively destroyed. The result is a stellar interior that becomes simultaneously sodium-rich and oxygen-poor. A very similar process occurs with magnesium and aluminum. Protons slam into magnesium nuclei, converting them into aluminum. In the hottest environments, this cycle can run even further, turning that aluminum into silicon. This is why we see the magnesium levels fall as the aluminum levels climb. One is being directly transmuted into the other. The preservation of this signature is what makes globular clusters such incredible time capsules. The stars we see today that display these anti-correlations are the second generation. They formed from gas that was not pristine, but had been thoroughly polluted by the winds or ejecta from that first generation of massive stars. When that polluted gas cloud collapsed to form new stars, the unique sodium-oxygen and magnesium-aluminum ratios were locked into the star's composition from birth. Because these are low-mass stars with relatively calm outer atmospheres, their surface composition has remained largely unchanged for billions of years. They are, in effect, living fossils, their atmospheres preserving a frozen record of the nuclear processes that occurred inside their long-dead stellar ancestors. This allows us to perform a kind of cosmic archaeology, reading the elemental patterns in today's stars to reconstruct the specific temperatures and conditions inside stars that vanished before our solar system even formed. The intensity of these anti-correlations also tells a compelling story about the mass and power of the original polluting stars. The magnesium-aluminum anti-correlation, for instance, is particularly revealing. The nuclear reactions that convert magnesium to aluminum require even higher temperatures than those in the neon-sodium cycle. This implies that the polluter stars must have had incredibly hot interiors, which typically means they were very massive. In fact, the presence of strong aluminum enhancement in some clusters suggests that the first generation must have included true stellar behemoths, perhaps stars with masses 30 times that of our Sun or even greater. The variation we see from cluster to cluster, with some showing only the sodium-oxygen anti-correlation and others showing both, gives us a way to classify them based on the intensity of their early chemical enrichment. It paints a picture of the early cluster as a diverse stellar community, where the most massive members left the most powerful and distinct chemical imprints on the next generation, their nuclear legacies written in light for us to decode billions of years later. Now, within the vibrant but volatile downtown of a globular cluster, we find a process so extreme it can lead to a gravitational traffic jam of catastrophic proportions. This is the mystery of core collapse, a dramatic evolutionary phase where the cluster's very heart contracts into a knot of unimaginable density. While many clusters have a bright, concentrated center, a subset of them, like the spectacular Messier 15, have taken this to the absolute limit. Their cores have undergone a runaway instability, squeezing a significant fraction of their total mass into a region so tiny that if you were standing at its center, the night sky would be a solid sheet of starlight, with thousands of suns closer to you than our own sun is to its nearest neighbor. This isn't just a dense collection of stars. It's the stellar equivalent of a black hole's event horizon, a point of no return for the cluster's structural stability. The engine driving this incredible contraction is a profound thermodynamic process known as a gravitothermal catastrophe. Think of the cluster as a sealed, self-gravitating container of gas, but in this case, the gas is made of individual stars. In any such system, heat naturally flows from the hot core to the cooler outer regions. For a star cluster, heat is actually the random motion of stars, their kinetic energy. In the cluster's core, where the density is highest, stars are constantly whizzing past each other, gravitationally interacting. These encounters act like a series of tiny nudges, slowly transferring kinetic energy from the inner stars to the outer ones. The core stars, having lost energy, slow down. And according to the laws of gravity, when an object in orbit loses energy, it falls inward. So, as the core loses heat, it contracts, growing even denser and hotter. This increased density, paradoxically, makes the heat transfer to the halo even more efficient, which causes further core contraction. It's a vicious, runaway feedback loop. The core heats up by contracting, but that heat is rapidly siphoned away, forcing it to contract even more to maintain equilibrium. Without a mechanism to stop it, this cycle would theoretically continue until the core reached infinite density, a physical impossibility that signals our understanding of the dynamics is incomplete. This is where the cluster's most resilient residents come to the rescue. Just as the core is on the brink of catastrophic collapse, a savior emerges from the chaos, binary star systems. In the extraordinarily dense environment of a collapsing core, the formation of binary stars is not just likely, it's inevitable. Single stars can be gravitationally captured by each other to form new pairs, or previously wide binaries can have their orbits tightened by close encounters with a third star. These binary systems become the cluster's thermal batteries. When a fast-moving single star has a close encounter with a tight binary, a complex gravitational dance occurs. The most common outcome is that the binary pair absorbs some of the single star's kinetic energy, effectively heating up, while the single star is flung away at a much higher speed, like a slingshot firing a projectile. This process does two critical things. First, the high-speed star carries away excess energy from the core, which actually helps the cooling process. But second, and more importantly, the hardening of the binary, the tightening of its orbit, stores a tremendous amount of binding energy. Think of it as compressing a spring. This stored energy acts as a central heating source for the core. As more and more binaries form and harden, they release this stored gravitational energy back into the stellar environment through further interactions, effectively pumping heat back into the core and halting its relentless collapse. This leads to one of the most astonishing revelations. Core collapse may not be a one-way street. The prevailing theory suggests that the life of a cluster's core is cyclical. It goes through long phases of gradual contraction and collapse, followed by a sudden bounce and re-expansion, driven by the energy output from these binary star interactions. Once the core has contracted to a critical density, the binary heating becomes so efficient that it overwhelms the cooling process. The core, now being pumped full of energy, begins to push back against gravity, causing it to re-expand. This expansion continues until the core density drops, the binary formation rate slows, and the cycle begins anew. Over the lifetime of a cluster, it may experience several of these collapse and bounce cycles, each one reshaping its internal structure. This dynamic equilibrium explains why we don't see clusters with infinitely dense cores. The binary stars provide a natural regulatory mechanism, a cosmic thermostat that prevents total gravitational catastrophe and gives these ancient cities a way to renew themselves from within, ensuring their survival across billions of years of cosmic evolution. But the dynamic nature of globular clusters doesn't just reveal itself through stellar collisions and black hole mergers. It also announces its presence through a brilliant, high-energy light that was completely unexpected. When X-ray telescopes first turned their gaze toward these ancient stellar cities, astronomers anticipated a quiet scene. After all, these are populations of old, stable stars, most of which should be peacefully burning their fuel without much violent drama. The reality was a shock. The cores of many globular clusters were glowing intensely with low-energy X-rays, hosting dozens and sometimes even hundreds of these point sources. The number of bright X-ray objects was hundreds of times greater per star than what we find in the general galactic field around our sun. This wasn't a faint, diffuse whisper. It was a vibrant, energetic chorus, and it pointed directly to the most intimate and volatile relationships stars can have. The primary source of this unexpected glow is a specific and exotic class of binary star systems. In each one, a stellar remnant, a white dwarf, a neutron star, or a stellar mass black hole is locked in a tight gravitational embrace with a normal, hydrogen-rich companion star. These pairs orbit so closely that their gravitational connection becomes a one-way street for material. The immense gravity of the dense remnant pulls gas from the outer layers of its companion star. This stream of stolen matter doesn't just fall directly onto the remnant. Instead, it forms a spinning, flat disk of superheated gas called an accretion disk. As the gas spirals inward through this disk, it is compressed and heated to temperatures of millions of degrees, becoming so hot that it emits not visible light, but powerful X-rays. It's a cosmic robbery happening on a grand scale, where the thief is so brilliant it lights up the cluster in a high-energy signature we can detect from Earth. So why are these volatile couples so common in globular clusters and so rare in the galactic suburbs? The answer lies entirely in the extraordinary population density. In our neighborhood, stars are so far apart that the chance of two specific stars forming a binary system is relatively low, and the probability of that system containing the exact right pairing of a stellar remnant and a donor star is lower still. But within the core of a globular cluster, stars aren't just neighbors. They are roommates in an overcrowded apartment. This constant proximity creates three distinct pathways to form these luminous X-ray binaries. The first is through direct stellar encounters. A solitary neutron star or black hole drifting through the core can pass so close to a normal star that they become gravitationally captured, forming a new binary pair on the spot. The second method involves the hardening of existing wide binaries. A binary system containing, say, two sun-like stars can have its orbit dramatically altered if a dense stellar remnant passes nearby. The gravitational interaction can eject one of the original stars and leave the remnant bound to the other, creating the perfect ingredients for an accretion-powered duo. The third, more gradual process is through dynamical friction. We've already seen how the heaviest objects sink to the center. This includes stellar remnants. As they congregate in the core, their chances of finding a partner through one of these gravitational games increase exponentially. The type of X-ray source we see depends heavily on the nature of the accreting object. Systems with a white dwarf, called cataclysmic variables, often produce predictable outbursts as accumulated hydrogen on the dwarf's surface ignites in a thermonuclear explosion. Those with neutron stars or black holes, known as low-mass X-ray binaries, can generate a steadier, more powerful X-ray glow as the immense gravity of the remnant crushes the infalling material. The sheer abundance of these systems makes globular clusters unparalleled natural laboratories for studying the end stages of stellar evolution and the extreme physics of accretion. This unexpected X-ray glow is therefore far more than just a pretty light show. It is the direct, observable proof of the intensely social lives of stars. It shows us that in the crowded downtown of a globular cluster, stellar relationships are not just common, they are the driving force behind some of the most energetic and persistent phenomena in the cosmos. Yet, for all the violent interactions and intense energy we've uncovered, there is a strange and echoing silence when it comes to one of the universe's most dramatic events. If globular clusters are such dynamic stellar cities, home to hundreds of thousands of stars, why have we never witnessed the aftermath of a recent, colossal core collapse supernova within one? This is the mystery of the missing supernova, a profound quiet that speaks volumes about the unique life cycle of these ancient systems. Unlike the bustling spiral arms of our galaxy, where massive stars are constantly being born and dying in brilliant explosions, globular clusters are retirement communities for stars, and the era of their most spectacular deaths is a chapter that closed billions of years ago. The primary explanation for this silence lies in the simple, brutal logic of stellar evolution. A core collapse supernova is the final, cataclysmic death rattle of a truly massive star, one at least 8 times heavier than our Sun. These stellar giants are the rock stars of the cosmos. They live fast, burn bright, and die young, exhausting their nuclear fuel in just a few tens of millions of years. Globular clusters, however, are ancient beyond comprehension. The last massive star capable of such a dramatic exit died when the universe itself was in its infancy, over 12 billion years ago. All the stars that remain today are the long-lived, slower-burning lower-mass stars, the stellar equivalent of a patient, long-enduring civilization whose fiery revolutionary period is a distant, faded memory. The clusters we observe are in a state of advanced, peaceful senescence, where the only stellar deaths are the quiet, gradual ones of stars like our Sun, which will gently puff away their outer layers to form planetary nebulae, leaving behind a white dwarf to slowly cool for eons. But what about the evidence of those ancient, titanic explosions? Couldn't we find the remnants, the expanding shells of gas, or the telltale pulsars, left over from that violent early era? This is where the second part of the puzzle comes into play, the relentless environmental cleanup of the cluster itself. Imagine a supernova exploding in the dense core of a young globular cluster. The initial blast would be unimaginably powerful, hurling the star's enriched outer layers outward at thousands of kilometers per second. This ejecta, a cloud of newly forged heavy elements, would initially form a supernova remnant, a bubble of hot gas expanding into the surrounding space. However, in a cluster, this surrounding space is not the near vacuum of the galactic halo. It is filled with the dense interstellar medium of the cluster itself, a tenuous but pervasive sea of gas. The expanding remnant would quickly slam into this material, slowing down and losing its coherent structure. Furthermore, the cluster is not a static environment. It is orbiting the galaxy, and as it plows through the galactic halo, any lingering, diffuse gas, including the scattered remains of ancient supernovae, would be effectively scooped up and stripped away by a process called ram pressure, much like dust being swept from a car moving at high speed. Over billions of years, any distinct, recognizable remnant of those early explosions would have been utterly dissipated, its material diluted and mixed back into the general pool of the galactic halo, leaving no distinct shell or structure for our telescopes to identify today. This doesn't mean those supernovae left no trace at all. Their legacy is simply written in a different language. The most direct evidence for their past occurrence is the population of stellar remnants they left behind. The violent core collapse of those massive stars is what created the very neutron stars and black holes we now find hiding in the clusters. Many of the millisecond pulsars we detect, those rapidly spinning neutron stars, are the spun-up corpses of those early giants. Furthermore, the chemical pollution we see in the multiple stellar populations, the extra sodium, aluminum, and other elements had to come from somewhere. While the slower winds from asymptotic giant branch stars contributed, the rapid injection of iron, oxygen, and silicon into the cluster's gas required the more violent and immediate trigger of supernova explosions. These ancient blasts were the primary polluters that seeded the material for the second generation of stars. So, while we cannot point to a specific, glowing ring of gas and call it a supernova remnant, the entire chemical and dynamical fabric of the cluster is, in fact, the ultimate supernova remnant. The missing supernova are not truly missing. They have simply faded into the background, their explosive contributions now frozen into the light of billions of stars and the invisible presence of the dark remnants that now govern the cluster's heart. Yet, even with this understanding of their violent and cyclical internal dynamics, we have barely scratched the surface of the true complexity of motion within these ancient cities. For a long time, it was tempting to picture a globular cluster as a simple, spherical swarm of stars, all swarming around a common center of gravity in random, unordered orbits, like a cloud of bees. But recent, precise measurements of stellar motions have completely shattered that simple image, revealing a kinematic tapestry of astonishing intricacy. These are not tranquil, orderly systems. They are dynamic ecosystems where the orbits of hundreds of thousands of stars tell a story of a chaotic and violent birth. The first major surprise was the detection of significant overall rotation in many clusters. Instead of being perfectly isotropic balls, these clusters often spin, much like a galaxy, but on a vastly smaller and denser scale. This rotation isn't always aligned in a simple way either. Some clusters exhibit complex rotational patterns, with their inner and outer regions spinning at different rates, or even in slightly different directions. This discovery was a major clue because such organized motion doesn't just appear by chance. It is a fossilized relic of the cluster's very formation. The prevailing theory for the origin of this spin is that it was inherited from the colossal, turbulent cloud of gas that collapsed to form the cluster billions of years ago. Just as an ice skater spins faster by pulling in their arms, as that primordial gas cloud contracted, any small, initial twist would have been amplified into the coherent rotation we can still measure today. This means that by studying a cluster's spin, we are effectively reading the angular momentum of the cloud from which it was born, a direct window into the conditions of the early universe. But the kinematic surprises don't stop at simple rotation. In the cores of some of the most massive clusters, like the magnificent Omega Centauri, astronomers have noticed something even more peculiar. The stars in the very center are moving at incredibly high velocities, whizzing around as if under the influence of a gravitational anchor of immense, concentrated mass. The most compelling explanation for this frenzied central dance is the presence of an intermediate mass black hole. This is a class of black hole that has long been theorized, but is incredibly difficult to confirm, with a mass thousands of times that of our Sun, bridging the gap between the stellar mass black holes formed from collapsing stars and the supermassive behemoths that lurk in galactic centers. The gravitational pull of such a hidden monster would naturally force the nearby stars into these high-speed orbits. Finding one of these intermediate mass black holes in a globular cluster would be a monumental discovery, as it could provide a crucial missing link in our understanding of how supermassive black holes grow. One theory suggests that these intermediate mass black holes could have served as the initial seeds that, through eons of mergers and accretion in the crowded early universe, eventually grew into the galactic giants we see today. Their potential presence in globular clusters transforms these systems from simple stellar collections into possible cradles for the birth of the most massive objects in the cosmos. Perhaps the most telling kinematic discovery, however, is the existence of multiple, distinct subpopulations of stars, each moving in its own unique way. This goes far beyond the chemical differences we discussed earlier. Using powerful observatories, astronomers can now measure the precise velocities of individual stars and have found that the different chemical populations, the first generation and the second, polluted generation, often do not move alike. In many clusters, the second generation, the stars born from the enriched gas, are often found to be more centrally concentrated and to orbit in a more random, disordered fashion. Meanwhile, the first generation, the pristine stars, tend to occupy the outer regions of the cluster and often move on more elongated or radial orbits. This kinematic separation is a profound piece of the formation puzzle. It strongly suggests that the second generation of stars did not form throughout the entire cluster, but was born deep within its gravitational well from gas that had settled into the core. This polluted gas, having been shed by the first generation of massive stars, would have been naturally drawn to the center of the cluster's potential, and there it condensed to form the new stars. These second-generation stars were therefore born into a pre-existing, dense environment and have remained dynamically cool and centrally focused ever since. The first-generation stars, on the other hand, retain the kinematic signature of the cluster's initial, more extended structure. This layered motion is a direct fossil record, preserving the sequence of events from the cluster's infancy and providing concrete evidence that its formation was not a single monolithic collapse, but a more protracted and complex process. All of this kinematic evidence, the overall rotation, the potential central black holes, and the distinct motions of different stellar populations, points toward a single, dramatic conclusion. The globular clusters we see today may not be the pristine, singular entities we once thought. Instead, many of them might be the products of a messy, hierarchical formation history, potentially involving the merger of smaller subclusters in the chaotic early universe. Imagine the young galaxy, filled not with 100 independent giant clusters, but with thousands of smaller, denser stellar clumps. As these clumps swarmed around each other, their mutual gravitational attraction would have drawn them together, leading to collisions and mergers. When two or more of these smaller clusters merged, they would have brought together stars with different kinematic histories, each with their own slight rotation and orbital preferences. The violent process of merger would have stirred this stellar soup, erasing some of the original ordered motion, but imprinting a new, more complex kinematic signature. This scenario elegantly explains why we see such intricate and varied patterns of rotation and multiple kinematic populations. We are witnessing the final, blended product of a cosmic consolidation that occurred billions of years ago. The stars in a cluster like Omega Centauri, with its vast range of metallicities and complex internal motions, may not all be siblings from the same parent cloud, but rather cousins from several smaller families that were forcibly united in a dramatic act of galactic assembly, their combined motion telling a story of a far more violent and collaborative origin than we ever imagined. But this congregation of black holes in the cluster's core sets the stage for an even more dramatic and energetic phenomenon, one that connects these ancient star cities directly to the most violent events we can detect in the cosmos. This is the puzzle of binary black holes. How do these solitary cosmic predators, each a gravitational point of no return, manage to find a partner and form a stable, orbiting pair in such a chaotic environment? The answer lies in the relentless gravitational networking that defines life in the core, a process that makes globular clusters prime factories for the black hole mergers that ripple across the universe. The primary mechanism for creating these dark duos isn't a gentle courtship. It's a gravitational exchange forced by the extreme social density of the cluster. Imagine 3 black holes involved in a close, complex encounter. 2 of them might be a pre-existing binary system, while the third is a solitary interloper passing nearby. As the 3 bodies gravitationally jostle, energy and momentum are traded in a chaotic dance. The most likely outcome of this 3-body interaction is that the lightest of the 3 black holes gets unceremoniously ejected from the group at high speed, carrying away excess energy and leaving behind a new, tighter binary pair composed of the 2 heavier black holes. This process, known as a binary exchange, is an incredibly efficient way to create black hole pairs. The black holes don't need to form together from a binary star system. They can find each other later in life through these violent gravitational introductions. Alternatively, 2 single black holes can also become gravitationally captured directly if they pass close enough that their mutual attraction can overcome their high relative speed, a process made possible by emitting gravitational waves during the encounter itself. These dynamical formations are unique to dense environments and are the dominant source of the binary black holes we believe are thriving within these clusters. Once formed, these binary black holes aren't necessarily stable for long. Their orbits continue to be perturbed by future close encounters with other stars or black holes. These interactions often have the effect of hardening the binary, meaning the 2 black holes are pushed into an ever tighter, faster orbit. As they spiral closer together, their immense masses whipping around each other, they begin to lose orbital energy in a very specific way, by radiating it away as ripples in the fabric of spacetime itself, gravitational waves. This loss of energy is a one-way street, inevitably causing the black holes to draw closer and closer until they finally merge in a cataclysmic event that releases more power than all the stars in the observable universe combined for a brief, spectacular moment. It is this final, violent merger that observatories like LIGO and Virgo are designed to detect. This direct link makes globular clusters a primary candidate for the sources of many gravitational wave signals we've recorded. The properties of the mergers detected: the masses of the black holes involved, the spin orientations of their orbits, often carry the distinctive signature of a dynamical origin rather than a binary system that evolved in isolation. For instance, black holes from globular clusters can be more massive than those typically formed from isolated stellar evolution, as they can undergo multiple mergers over time, and their spins are often randomly oriented, a telltale sign of a chaotic pairing process. Every new gravitational wave detection from a black hole merger with these characteristics is a powerful piece of corroborating evidence, confirming that the theoretical drama we've envisioned within these clusters is not just a model, but a reality playing out on a cosmic scale. The silent, dark hearts of these ancient stellar cities are, in fact, some of the most active and prolific engines for generating the ripples in spacetime that allow us to listen in on the universe's most extreme events. Now we turn our attention to a fundamental cosmic ingredient that plays a surprisingly dramatic role in shaping the lives of stars within these clusters: helium. This simple, inert gas the second most abundant element in the universe, is far from a passive bystander. In the unique petri dish of a globular cluster, differences in helium abundance from one star to the next act as a powerful hidden variable, orchestrating a star's entire life story from its temperature and color to its ultimate fate. The key revelation is that the multiple generations of stars we've discussed aren't just different in terms of nitrogen or sodium. They possess profoundly different amounts of helium from the moment they are born. That second generation, formed from gas polluted by the first, often starts life with a significantly enriched helium content. This initial condition is a game changer because helium is heavier than hydrogen. A star born with extra helium has a denser, more compact core from its very first fusion reactions. This compactness forces the star to burn its nuclear fuel at a higher temperature and a faster rate. The consequences are visible across the cluster's entire population. For stars on the horizontal branch, that stable phase of helium burning, a boost in initial helium content, is like turning up the thermostat. A helium-rich star will enter this phase burning hotter and brighter, positioning itself on the blue, more extreme end of the horizontal branch. This simple fact provides a powerful explanation for why some clusters of the same metallicity have such dramatically different horizontal branch morphologies. The one with a stronger second generation of helium-enriched stars will naturally display a longer, bluer tail of hot stars, directly addressing the long-standing second parameter problem. The helium enigma also extends to the phenomenon of blue stragglers. While collisions and binary interactions are the primary formation mechanisms, the internal structure of the resulting star is critically dependent on its helium content. A blue straggler formed from the merger of two helium-rich stars would be a fundamentally different object, hotter, more luminous, and potentially shorter-lived than one formed from two pristine, helium-poor stars. This helps explain the diversity we observe even among these revived stars. The great challenge, however, lies in measuring this crucial element. Unlike sodium or iron, whose signatures are relatively easy to read in a star's spectrum, helium is notoriously shy. Its primary spectral lines appear only in the hottest stars, and even then, they are faint and difficult to observe with precision. Astronomers must therefore become cosmic detectives, inferring helium abundance indirectly by studying its effects on other, more easily measurable stellar properties, or by finding just the right type of hot star in a cluster to analyze. This makes helium the ghost in the machine of globular cluster evolution, an elusive but utterly essential component whose subtle variations write themselves across the brilliant and varied tapestry of the cluster's stellar population. And just as we've seen how stars within a cluster can collide and merge, our galaxy itself has been engaged in a similar act of cosmic consumption on a vastly grander scale. The very globular clusters orbiting the Milky Way are not all native-born citizens. Many are celestial immigrants, captured from smaller galaxies that our own devoured long ago. This is the story of galactic cannibalism, a process where large galaxies grow by tearing apart and absorbing their smaller neighbors, and the evidence is written in the distinct identities of these ancient star clusters. When astronomers began meticulously cataloging the globular clusters in our galaxy's halo, the vast, sparse sphere of stars and old clusters surrounding the main disk, they noticed something perplexing. These clusters didn't all share a uniform history. While many are incredibly ancient and metal-poor, as expected for objects that formed with the Milky Way itself, others have startlingly different ages and chemical compositions. Some are noticeably younger, and some possess metallicities that are completely out of sync with the native halo population. This was a glaring clue that these clusters could not have all been born in the same cosmic nursery. They were interlopers, and their presence points to a violent and dramatic history of galactic mergers. The most famous and compelling example of this is the ongoing destruction of the Sagittarius dwarf spheroidal galaxy. This tiny satellite galaxy has been locked in a gravitational dance with the Milky Way for billions of years, and with each close pass, our galaxy's immense tidal forces have been systematically stripping it apart. The stars and clusters of the dwarf galaxy are being torn from its grasp and woven into the fabric of our own halo, creating a great stream of debris that wraps around the Milky Way. Astronomers have definitively linked several globular clusters to this carnage, including M54, which is now believed to be the former core of the Sagittarius dwarf itself. Imagine that what we once thought was just another globular cluster in our collection is actually the heart of a conquered galaxy, a king dethroned and absorbed into a larger empire. The chemical fingerprint of M54 and its associated clusters matches that of the Sagittarius stream, not the native Milky Way clusters, providing a smoking gun that directly ties them to this external source. But the evidence doesn't stop there. Other clusters, like NGC 2808, show kinematic signatures, specific paths and velocities that are completely distinct from the rest of the halo population. They are moving in retrograde orbits, going against the flow of most other objects, a clear sign that they were acquired from outside, likely from a different dwarf galaxy that was consumed even earlier in the Milky Way's history. By grouping these alien clusters based on their shared motions and chemistries, astronomers can perform a kind of celestial archaeology, tracing them back to their original parent galaxies, even though those galaxies were completely dismantled and digested eons ago. These clusters are the enduring fossils of those ancient galactic meals. Each family of clusters with a unique origin story represents a separate accretion event, a chapter in the growth of our galaxy. This reveals that the Milky Way did not form in majestic isolation. It was built through a series of violent mergers, a hierarchical assembly where smaller building blocks were relentlessly drawn together by gravity. This process of galactic cannibalism transforms our understanding of a globular cluster's role in the cosmos. They are not just passive inhabitants of a galaxy. They become incredibly robust tracers of galactic evolution. Stars are often too faint and numerous to track back to a single source, but a globular cluster is a bright, coherent, and durable package. Its tightly bound gravity allows it to survive the violent process of its host galaxy being torn apart, often remaining intact for billions of years after the event. This makes clusters perfect tags, their age and metallicity acting as a permanent barcode that identifies their origin. By mapping the locations and motions of these captured clusters, we can effectively reconstruct the merger history of the Milky Way, pinpointing when and from which direction these ancient collisions occur. The fact that we see these captured clusters predominantly in the halo is also telling. It underscores that the halo is not a pristine relic, but a dynamic graveyard and a living record of the Milky Way's cannibalistic past, a cosmic museum built from the remains of galaxies that no longer exist. This evidence firmly establishes that the growth of large galaxies like our own is a fundamentally predatory process, and the silent, ancient globular clusters are the most enduring witnesses to this billion-year drama of construction and destruction. Yet even as we map the remnants of devoured galaxies, a more elusive and controversial possibility emerges, that some of these dense stellar systems might be hiding a secret ingredient that could redefine their very nature. We are now venturing into the realm of the dark globular cluster candidates, objects whose gravitational influence suggests they contain far more mass than their visible stars can account for, pointing to the potential presence of that most mysterious of cosmic components, dark matter. For the classic globular clusters we've explored, dark matter has never been part of the story. Their gravitational stability is thought to be entirely explained by the collective pull of their stars, stellar remnants, and a small amount of leftover gas. They are considered baryon-dominated, meaning their gravity comes from normal matter. The idea that a dense, spherical swarm of stars could be permeated by a massive halo of dark matter is a radical departure from everything we thought we knew about their formation. If proven true, it would mean that some of these objects are not the simple, ancient relics we believe them to be, but something entirely different, cosmic chimeras with a hidden, dark heart. One of the most compelling candidates stirring this debate is a system known as NGC 2407. When astronomers measured the velocities of its stars, they found something perplexing. The stars were moving so quickly that the cluster's own gravity, based solely on the light of its stars, shouldn't have been strong enough to hold them together. It should have flown apart eons ago. The simplest explanation for this discrepancy is the presence of unseen mass, a dark matter halo, providing the extra gravitational glue to keep the system bound. Another intriguing object is Palomar 14, an exceptionally faint and diffuse cluster in the outer reaches of our galaxy's halo. Its stars are so widely spaced that, according to conventional models, it too should have been ripped apart by the Milky Way's tidal forces. Its continued existence is a puzzle that a significant dark matter component could elegantly solve, acting as a stabilizing anchor against the galaxy's disruptive pull. The primary challenge in confirming these dark candidates lies in the delicate art of weighing something you cannot see. Astronomers use the velocities of stars as a cosmic scale. By carefully measuring how fast stars are moving within the cluster, they can calculate the total mass required to keep those stars from escaping. They then compare this total mass to the mass-to-light ratio, the mass calculated from the cluster's brightness. A normal globular cluster has a mass-to-light ratio of around 1 or 2, meaning its mass is roughly what you'd expect from its starlight. A candidate like NGC 2407, however, has a ratio that appears to be significantly higher, suggesting the presence of substantial dark matter. The problem is that these measurements are incredibly difficult. A cluster's velocity dispersion, the range of speeds of its stars, can be easily inflated by a few unseen binary star systems, where the orbital motion of a pair of stars mimics the high velocity of a single star. Furthermore, many of these candidate clusters are being actively torn apart by the galaxy's tides, and this tidal disruption can also stir up the stars, making them appear to move faster and mimicking the signal of dark matter. Disentangling these dynamical effects from a genuine dark matter signal is at the very forefront of observational astronomy. If these candidates are confirmed, the implications would be nothing short of revolutionary for our understanding of how such structures form. The leading theory for why classic globular clusters lack dark matter is tied to their violent birth in the early universe. They are thought to have formed within small, dense pockets of gas that were rapidly compressed by the intense pressure waves from nearby supernova or cosmic turbulence. In this scenario, the dark matter, which interacts only through gravity and not with the gas, would have been left behind as the normal matter collapsed to form the dense star cluster. A globular cluster with a dark matter halo simply doesn't fit this picture. Instead, it points toward a completely different origin story, that these objects are not true globular clusters at all, but the stripped-down nuclei of ancient dwarf galaxies. Imagine a small dwarf galaxy, itself embedded in a massive halo of dark matter, venturing too close to a giant like the Milky Way. The galaxy's outer stars and dark matter are progressively stripped away by tidal forces over billions of years, leaving behind only its most resilient central component, a dense, star-packed core that looks, for all intents and purposes, like a globular cluster. This remnant would still be cloaked in the vestiges of its original dark matter halo, a ghostly fingerprint of its more glorious past. This scenario elegantly connects the dark cluster puzzle to the phenomenon of galactic cannibalism we just explored. It suggests that among the hundreds of globular clusters orbiting our galaxy, there could be a population of these galactic imposters objects that masquerade as simple star clusters, but are in fact the fossilized hearts of galaxies we consumed long ago. The search for dark globular clusters is therefore more than just an accounting of mass. It is a hunt for the minimal survivors of galactic destruction, the last enduring testament to the first building blocks of the cosmos. But just when we thought we had a handle on the energetic X-ray glow from binary systems, astronomers pointed their telescopes toward a handful of globular clusters and found something that outshone them all. Objects so brilliant in X-rays, they defied a fundamental limit of physics. These are the ultraluminous X-ray sources, or ULCs, and their discovery within the ancient confines of globular clusters sent shockwaves through the astrophysics community. A typical stellar mass black hole or neutron star, accreting matter from a companion, has a theoretical maximum brightness known as the Eddington limit. This is the point where the outward pressure from the intense radiation being generated actually pushes back against the inward flow of material, creating a balance that caps how luminous the object can become. But ULX is blow right past this limit, shining hundreds or even thousands of times brighter than the Eddington limit for a typical stellar remnant. Finding these cosmic overachievers in globular clusters was especially puzzling because it meant that the engines powering them weren't the supermassive black holes found in galactic centers, but something much smaller and far more mysterious, operating in a way we thought was impossible. The leading theory points to a perfect storm of conditions that can only occur in such a densely packed environment. Imagine a stellar mass black hole, perhaps 10 times the mass of our Sun, locked in a tight orbit with a generous donor star. In the crowded core of a globular cluster, this binary system is constantly being fed. Close encounters with other stars can perturb its orbit, shoving the companion star closer and dramatically increasing the rate at which its outer layers are siphoned away. This creates a supercharged accretion flow, a veritable fire hose of gas streaming onto the black hole's disk. Under normal circumstances, the radiation from this process would be expected to stem the flow, but physicists now believe that if the accretion rate is high enough, the disk of material can undergo a radical transformation. It may puff up into a thick, dense, funnel-like structure where the intense radiation is trapped and channeled out through the top and bottom of the funnel rather than pushing radially outward. This allows vast amounts of material to plunge onto the black hole without being blown away, effectively allowing it to violate its own Eddington limit and shine with ultraluminous intensity. It's a bit like overloading a furnace with fuel and modifying its chimney to handle the extreme exhaust. The result is a brilliance that shouldn't be possible under standard rules. Another compelling possibility is that the black holes at the heart of these ULXs are not your average stellar mass variety. The dynamic environment of a globular cluster is a perfect breeding ground for building heavier black holes through successive mergers. A black hole formed from a stellar collapse can, over billions of years, merge with another, and then another, creating an intermediate mass black hole weighing in at a few hundred to a few thousand solar masses. This changes the entire energy equation. The Eddington limit scales with mass, so a black hole that is 100 times more massive than the Sun has an Eddington limit 100 times higher. What appears as an ultraluminous output for a small black hole could be comfortably sub-Eddington for a more massive one. The presence of an intermediate mass black hole accreting at a modest rate could perfectly explain the steady, dazzling X-ray flux of a ULX, providing an elegant solution to the brightness puzzle. while simultaneously offering some of the best indirect evidence for these elusive middle-weight black holes. The neutron star scenario, however, is perhaps the most mind-bending of all. We have since discovered that several extragalactic ULXs are actually powered by neutron stars, as evidenced by the detection of pulsations and cyclotron lines in their X-ray spectrum. This is even more counterintuitive, as neutron stars are smaller and have an even lower theoretical Eddington limit than stellar mass black holes. For a neutron star to achieve such incredible luminosity, its magnetic field may play a crucial role. A neutron star with an immensely powerful magnetic field could have accretion channels that guide material directly onto its magnetic poles. The column of infalling gas crashes onto a relatively small area at nearly the speed of light, and the resulting release of energy is so concentrated that it can break the Eddington limit locally, creating hotspots of extreme brightness without immediately halting the overall flow of material. This suggests we are witnessing a different mode of accretion altogether, one where the rules are rewritten by unimaginable magnetic forces. The discovery of ULXs in globular clusters, therefore, does more than just add another exotic object to their inventory. It forces a fundamental revision of our understanding of how matter behaves under the most extreme gravitational and magnetic conditions, proving that these ancient stellar cities are home to some of the most efficient and powerful energy conversion engines in the universe. And now we turn to one of the most speculative and electrifying possibilities in modern astronomy, a potential connection between the serene, ancient cities of globular clusters and the most enigmatic, fleeting explosions of energy in the cosmos, fast radio bursts. For years, FRBs have captivated and confounded scientists. These are not gentle signals. They are colossal blasts of radio waves that last for mere milliseconds. Yet in that instant, they can release more energy than our sun emits over several days. Their origins have been one of the great cosmic detective stories, with suspects ranging from evaporating black holes to advanced alien civilizations. But recently, a compelling new suspect has emerged from the shadows: the dense, neutron star-rich environments of globular clusters. The logic behind this connection is as compelling as it is straightforward. To produce such an immense burst of energy in such a vanishingly short time, you need an engine of incredible power operating under the most extreme physical conditions imaginable. Neutron stars, the ultra-dense, city-sized corpses of massive stars, fit this description perfectly, and globular clusters, as we've discovered, are veritable nurseries for these exotic objects. Through countless stellar interactions and dynamical processes, clusters can accumulate a significant population of neutron stars, including the rapidly spinning, highly magnetized variety known as magnetars. It is within the chaotic, crowded core of a cluster that the perfect storm for an FRB might be brewing. One of the most promising mechanisms involves a magnetar experiencing a starquake. Picture a neutron star with a crust of iron nuclei packed into a rigid, crystalline lattice, all under the strain of an unimaginably powerful magnetic field, a field trillions of times stronger than Earth's. This magnetic stress can cause the star's crust to suddenly crack and shift, a seismic event on a cosmic scale. This starquake releases a tremendous amount of magnetic energy in a fraction of a second, energizing the plasma surrounding the star and launching a shock wave that ripples outward at nearly the speed of light. As this shock propagates, it can coherently emit a brilliant flash of radio waves, a fast radio burst. The dense environment of a globular cluster makes such events more likely. The constant gravitational nudges from passing stars could provide the extra trigger needed to destabilize a magnetar's crust, pushing it past its breaking point and initiating a quake. It's a scenario where the relentless social dynamics of the cluster directly enable one of the universe's most violent, albeit brief, outbursts. But starquakes are not the only game in town. The crowded core also dramatically increases the chances of neutron stars finding each other. In the dynamic dance of the cluster, a binary system comprising two neutron stars could have its orbit tightened over eons through gravitational interactions with other stars. As these two ultra-dense objects spiral ever closer, they could potentially merge, while the final merger itself is the source of gravitational waves and a kilonova explosion. The pre-merger phase is a cauldron of intense magnetic activity. The interaction between the two stars' immensely powerful magnetic fields during their final moments could, in theory, generate a short, incredibly powerful radio burst just before they collide. This would link the phenomena of FRBs directly to the same cosmic factories that produce gravitational waves and forge heavy elements like gold and platinum. While we have not yet definitively observed an FRB from a globular cluster, the circumstantial evidence is building. The recent localization of a repeating FRB to a globular cluster in a distant galaxy was a monumental moment, sending ripples of excitement through the astrophysical community. While that particular cluster is not an old, classic globular like those in the Milky Way, its dense, ancient stellar environment shares the key ingredients that make the FRB connection so plausible. This discovery powerfully suggests that the unique conditions within these massive, old star clusters are indeed capable of producing these mysterious signals. By focusing our radio telescopes on the globular clusters orbiting our own galaxy and those in nearby systems, we are essentially monitoring the most likely cosmic neighborhoods for these spectacular flashes to occur. Unlocking the FRB mystery could therefore provide us with a powerful new tool. Because these bursts travel across vast cosmic distances, they interact with the tenuous gas between galaxies. By studying how the burst signal is dispersed, astronomers can effectively weigh the invisible atomic matter in the cosmos, mapping the large-scale structure of the universe in a way that was previously impossible. The humble globular cluster, once seen as a simple relic, may hold the key to calibrating this new cosmic yardstick, proving once again that the smallest, densest structures can illuminate the grandest scales of existence. Now, this chemical detective story leads us to one of the most specific and telling clues in the entire mystery, a particular anomaly that stands out even among the bizarre patterns we've already seen. While the sodium-oxygen anti-correlation is widespread, astronomers have discovered that in certain clusters, the situation becomes even more extreme, with some stars exhibiting a truly staggering overabundance of nitrogen. This isn't just a slight enrichment. We're talking about nitrogen levels that can be hundreds or even thousands of times greater than what we find in a typical star like our Sun. This nitrogen-rich anomaly is like a screaming fingerprint left at the scene of a cosmic crime, and it points directly to a very specific, high-temperature nuclear process that must have occurred inside the very first stars to light up these clusters. To understand why this nitrogen spike is so revealing, we need to look at a fundamental cycle of nuclear fusion that powers massive stars, known as the CNO cycle. In stars much heavier than our Sun, the primary way hydrogen is fused into helium isn't through the direct proton-proton chain, but through a more complex catalytic process that uses carbon, nitrogen, and oxygen as intermediate steps, hence the name CNO cycle. In its initial phase, the cycle uses carbon-12 as a catalyst. A proton slams into the carbon nucleus, turning it into unstable nitrogen-13, which quickly decays into stable carbon-13. Another proton collision creates nitrogen-14. This is where the crucial part happens. Under normal, balanced conditions inside a stable star, the cycle would proceed further, converting that nitrogen-14 into oxygen-15, and then back to carbon-12, completing the loop. However, if the conditions are just right specifically, if the temperature is high enough but not so high that the cycle runs to completion, the process can get effectively stuck at the nitrogen-14 step. The carbon that entered the cycle gets converted into nitrogen and then just sits there, accumulating. For this to happen on a grand scale, the material needs to be processed at temperatures between 20 and 30 million Kelvin and then be expelled from the star before it can be cycled further. This partial CNO cycle processing is the only known way to produce the colossal nitrogen overabundances we observe, and it tells us that the polluting stars not had hot interiors, but that their internal layers were mixed in a very specific way to allow this nitrogen-rich material to be ejected. So, which of the first-generation stars were capable of this precise feat? The usual suspects, the asymptotic giant branch stars and the massive, fast-rotating stars, are back in the spotlight, but the nitrogen clue forces us to refine our search. For the asymptotic giant branch stars, the key is a process called hot bottom burning. In the most massive AGB stars, those between about 4 and 8 times the mass of our Sun, the base of the convective envelope that surrounds the core becomes incredibly hot. So hot, in fact, that the CNO cycle can actually occur right there in the envelope. As convection constantly churns the star's outer layers, material is cycled down to this hot bottom, where carbon is rapidly converted into nitrogen. The convection then dredges this newly forged nitrogen up to the surface, where it is finally expelled into space through strong stellar winds. This provides a slow, steady, and highly efficient method for polluting the cluster's gas with enormous amounts of nitrogen. The other prime candidate, the massive fast rotators, offers a more violent alternative. A very massive star, spinning at breakneck speed, can have its interior stirred so thoroughly that the partially processed nitrogen from the core regions is mixed throughout its vast volume and then flung out into space by centrifugal force, again seeding the environment with this specific elemental signature. The presence of these nitrogen-rich stars, therefore, acts as a powerful cosmic filter. It allows astronomers to rule out certain types of polluters and zero in on the most likely culprits. For instance, it heavily implicates the more massive AGB stars over the lower mass ones, as the lower mass stars never achieve temperatures high enough for hot bottom burning. Similarly, it suggests that the fast rotators needed to be truly massive to generate the required internal conditions. This nitrogen anomaly becomes a critical diagnostic tool, helping us to piece together the mass range and the specific evolutionary pathways of the stars that shaped the chemical landscape of the cluster billions of years before our own solar system even existed. It transforms these ancient, glittering stars from simple points of light into precise astronomical instruments, their atmospheres preserving a frozen record of the nuclear fires that burned in their long-vanished ancestors. And this journey into the most energetic corners of globular clusters now brings us to a discovery that is fundamentally reshaping our understanding of stellar death itself. For decades, astrophysicists operated with a seemingly clear yet puzzling boundary in the cosmos. On one side, we had neutron stars, the ultra-dense remnants of collapsed stellar cores, with observed masses capped at around 2.2 times the mass of our Sun. On the other side, we had stellar mass black holes, which seemed to start at approximately 5 solar masses. This left a conspicuous void between them, a celestial no-man's land known as the mass gap. The question was profound. Why did nature appear to avoid creating compact objects with masses between 2.2 and 5 times that of our Sun? Was this a fundamental limit of physics, or was it simply an observational blind spot? The answer, it turns out, may have been hiding in the dense stellar environments of globular clusters all along. and we are now finding it through the ripples in spacetime they create. The traditional explanation for this gap was tied to the violent physics of supernova explosions. The theory suggested that when a massive star dies, the core collapse is so energetic that it blasts away the star's outer layers. For a star to leave behind a remnant in that 2 to 5 solar mass range, the supernova would need to be unusually weak, failing to eject enough material, or strangely fine-tuned. It was thought that stars either successfully exploded, leaving a neutron star below the gap, or failed completely, collapsing entirely into a black hole well above 5 solar masses. This clean dichotomy, however, was always a bit too neat, and the dynamic environment of globular clusters provides a perfect laboratory to challenge it. These clusters are cosmic melting pots where stellar remnants don't just sit in isolation. They constantly interact, merge, and are ejected. This dynamic history can completely scramble the initial mass distribution of black holes and neutron stars that the supernova produced, offering a new way to probe this mysterious territory. The breakthrough in filling this gap has come almost entirely from gravitational wave astronomy, when the LIGO and Virgo observatories detect the signature of 2 black holes merging. One of the first things scientists measure are their individual masses. Early detections seem to confirm the mass gap, with black holes consistently weighing in at over 5 solar masses. But then, as more data streamed in, tantalizing signals began to appear. Events like GW 190426, the merger of a black hole with a mass of about 2.6 solar masses with another, heavier object, sent a jolt of excitement through the community. Here was a compact object sitting squarely in the heart of the mass gap. Was it the lightest black hole ever found, or the heaviest neutron star? The data was ambiguous, but its very existence proved that the mass gap was not an impenetrable wall. And where do we suspect such unusual objects to form? The dynamical environment of globular clusters is a prime suspect. Within a cluster, a neutron star can collide with and consume another star, bulking up its mass through successive mergers. Alternatively, a black hole born from a supernova could be on the lighter end of the spectrum, and through gravitational wave observations, we are now catching these previously hidden populations. The process that creates these gap-spanning objects is a direct consequence of the cluster's relentless social dynamics. Imagine a typical neutron star, formed from a supernova and wandering through the cluster's core. Through a close gravitational encounter, it finds a partner, perhaps another neutron star, a white dwarf, or even a main sequence star, and forms a binary system. If the pair is tight enough, the neutron star can begin gravitationally stripping material from its companion, a process that gradually feeds mass onto its incredibly dense surface. This accretion can, over time, push the neutron star past its theoretical stability limit, causing it to collapse further into a low-mass black hole. This provides a direct channel to create an object with a mass of, say, 3 or 4 solar masses, an object that would have been very difficult to form from a single, isolated supernova. Even more dramatically, the outright collision and merger of 2 neutron stars can produce a remnant with a mass that falls directly into the gap. While such a merger often results in a black hole, there is a brief, crucial window where the resulting object could be a supermassive neutron star, a transient object that exists for only milliseconds before its own gravity overwhelms it. Alternatively, the merged object might stabilize as a black hole with a mass that neatly bridges the divide. These dynamical formation channels are like a cosmic assembly line for objects that nature seemed hesitant to produce through solitary stellar death. The implications of discovering these mass gap objects are profound, reaching far beyond simply cataloging exotic remnants. Each one is a crucial data point, that helps us understand the most extreme states of matter. The equation of state of neutron star matter, the relationship between its density and pressure, is one of the great unsolved problems in physics. By finding objects that push the upper limits of neutron star mass, we are effectively performing a stress test on this equation. Does matter inside a neutron star become a soup of free quarks and gluons at these incredible densities? Or does it remain as neutrons, a mass gap object that is definitively identified as a heavy neutron star would immediately rule out many proposed equations of state, telling us what is not possible inside these incredible objects? Conversely, finding a plethora of low-mass black holes suggests that the supernova mechanism is more complex and varied than our models predict, perhaps allowing for partial fallback that results in remnants of all sizes. The data flowing from globular clusters, both through direct observation and their contribution to the gravitational wave catalog, is providing the critical evidence we need to move from theoretical speculation to concrete understanding of what happens when a star's core collapses into the most dense form of matter the universe allows. Now, as we move from the colossal explosions and mergers that shape these clusters, we discover that some of their most vital secrets are revealed not in violent ends, but in the gentle, rhythmic pulsing of their most reliable residents, the peculiar and diverse family of variable stars. Within the ancient stellar populations of globular clusters, astronomers have identified a remarkable abundance of stars that rhythmically brighten and dim over predictable cycles. These aren't random flickers. They are the steady, luminous heartbeats of stars in a specific, unstable phase of their lives, and their predictable nature makes them one of the most powerful tools in the cosmic toolbox. The most famous of these are the RR Lyrae stars, often called the Old Faithfuls of the cosmos. These aging stars have exhausted the hydrogen in their cores and have moved into a stage where they pulsate with incredible regularity, swelling and contracting over periods of just a few hours to a day. Their true power lies in a remarkable property. All RR Lyrae stars of a certain type pulsating with the same period have roughly the same intrinsic brightness, or absolute magnitude. This makes them perfect standard candles, celestial lighthouses of known wattage. By measuring how dim they appear from Earth, astronomers can calculate their distance with remarkable precision. For decades, RR Lyrae stars have been the gold standard for measuring distances to globular clusters themselves, providing the first rung on the cosmic distance ladder that allows us to map the scale of our own galaxy and beyond. But the RR Lyrae stars are not the only pulsators lighting up these clusters. We also find their more luminous cousins, the type Roman II Cepheids. These stars are similar to the classical Cepheids used to measure distances to other galaxies, but they belong to the old, metal-poor population of the galactic halo and globular clusters. Their pulsation periods are longer, from 1 to over 50 days, and their greater luminosity makes them visible across vast intergalactic distances. Then there are the SX Phonesis stars, which are essentially the hotter, faster pulsating siblings of the RR Lyrae variables. Each of these classes of variable stars acts as a unique key, unlocking different doors in our understanding of the cosmos. Type Roman II Cepheids help us calibrate the distances to the clusters in the far outer halo of our galaxy, while the SX Phonesis stars provide a window into the physics of stars that are evolving off the main sequence. Together, this symphony of pulsating stars turns a globular cluster from a static picture into a dynamic orchestra, with each type of variable playing its own distinct rhythm, and all of them contributing to a grander understanding of cosmic scale and stellar life cycles. However, when astronomers began to listen closely to this cosmic orchestra, they noticed the music wasn't always perfectly in tune. The pulsation properties of these stars within clusters often show subtle but significant anomalies that aren't seen in their counterparts floating freely in the galactic field. For instance, the relationship between a variable star's pulsation period and its intrinsic brightness, the very foundation of its use as a standard candle, can be slightly different inside a cluster. An RR Lyrae star in a cluster might have a slightly different brightness for its pulsation period than a seemingly identical RR Lyrae star born in isolation. This isn't a flaw in the tool, it's a vital clue. These anomalies are caused by the unique environmental factors of the cluster itself. The most significant of these is the distinct chemical composition we've explored before. A star born from helium-enriched, polluted gas in a cluster's second generation will have a different internal structure than a pristine star of the same mass. Its core is denser and hotter, which affects how and why it pulsates. The pulsations of a variable star are driven by a delicate valve-like mechanism in its outer layers, where ionized helium becomes more opaque to light, trapping heat and causing the star to expand. When the star expands, it cools. The helium recombines, the opacity drops, and the star contracts again, restarting the cycle. The initial helium content of a star is a critical factor in this process. A helium-rich variable star will pulsate with a different period and a different luminosity than a helium-poor one, directly explaining why the standard period-luminosity relationship needs fine-tuning when applied to the complex populations of a globular cluster. Furthermore, the sheer age and evolutionary state of all stars in a cluster play a role. Because every star in an ancient cluster is roughly the same age, the variable stars we see are all at a very specific and advanced point in their evolutionary journey. They are all evolving along a very narrow path on the Hertzsprung-Russell diagram, meaning their masses and radii are more uniform than a random sample of variable stars in the galaxy. This uniformity is a boon for scientists, as it allows them to study the effects of other parameters, like rotation and magnetic fields, on the pulsation with fewer confounding variables. Some clusters even show multiple distinct groups of RR Lyrae stars with different properties, a direct reflection of the multiple stellar populations. You might find one group of RR Lyrae stars with normal pulsations that belong to the first generation, and another group with slightly different periods and amplitudes that belong to the helium-rich second generation. This allows astronomers to use the variable stars themselves as tracers of the cluster's complex formation history, their rhythmic light curves encoding a story of birth and pollution that occurred billions of years ago. Studying these peculiar variables in the crowded core of a cluster also presents a unique challenge that, when overcome, yields incredible rewards. The phenomenon known as the Blaschko effect, where the amplitude and period of an RR Lyrae star's pulsation are themselves modulated over a longer cycle of tens to hundreds of days, appears to be more common in clusters. The cause of this secondary modulation is still debated, but it may be linked to stellar rotation or resonant interactions between different pulsation modes within the star. In the dense cluster environment, the possibility exists that close gravitational encounters could spin up a star, altering its rotation rate and potentially triggering or influencing this Blaschko effect. By carefully disentangling the light of these pulsating stars from their thousands of neighbors, astronomers can probe these subtle effects, using them to test sophisticated models of stellar interiors. Each pulsation is like a sonar ping sent through the star's structure. By analyzing the tiny variations in the light curve, scientists can infer the star's density, temperature profile, and internal composition. The anomalies displayed by globular cluster variables are therefore not mere curiosities. They are precise diagnostics. They force us to refine our universal distance scale, and they provide a controlled laboratory for understanding how a star's chemical birthright and its dynamic environment shape its final rhythmic dance of light. a dance that continues to illuminate the darkest corners of cosmic measurement. We now arrive at a discovery that brings the cosmic story full circle, connecting these distant, ancient star cities directly to our own origins. For decades, the Sun has been viewed as an only child, a solitary star wandering the galactic field. But a growing body of evidence suggests a far more dramatic and communal birth. It is a compelling possibility that our own solar system was not born in isolation, but within a bustling stellar nursery, a young, massive cluster much like the ones we've been exploring, a place where our Sun had thousands of stellar siblings. The first, and perhaps most compelling, piece of evidence for this dramatic origin story comes not from the stars, but from ancient rocks right here in our solar system. Deep within some of the most primitive meteorites, those pristine leftovers from the solar system's formation, scientists have found a startling chemical signature. These meteorites contain tiny, anomalous grains of minerals that are enriched with specific radioactive isotopes, most notably a form of aluminum and a form of iron. The crucial detail is that these isotopes have very short half-lives. They decay completely in just a few million years. Their presence in meteorites means they must have been freshly forged and injected into our infant solar nebular right as it was condensing to form the Sun and planets. There is only one known event powerful enough to produce these specific isotopes in such abundance and shoot them into a nearby cloud of gas and dust, a supernova explosion. This points to a truly incredible scenario. As our solar system was taking shape, a massive, unstable stellar neighbor reached the end of its life and exploded, literally seeding our cosmic cradle with the radioactive elements that would later help heat and differentiate the early planets. In the relatively empty galactic environment where stars are born today, such a close and timely supernova would be an incredible coincidence, but within a dense, young globular cluster, it would be the norm. In such a crowded stellar metropolis, massive stars are common, and they live fast and die young. A supernova going off within a few light years of our protosolar nebula would not just be possible, it would be expected. The blast would have been a terrifyingly beautiful event, a cosmic forge that both polluted and potentially compressed our nebula, triggering the collapse that led to the Sun's ignition and gifting the solar system with the very elements that make rocky planets like Earth possible. This single piece of radioactive forensic evidence powerfully suggests our Sun's birthplace was a vibrant and at times violent stellar community. This revelation transforms the search for our Sun's lost family from a flight of fancy into a serious astronomical endeavor. If the Sun was born in a cluster, then over the 4.6 billion years since its formation, that cluster would have completed many orbits around the galaxy. The gentle but relentless tidal forces of the Milky Way, along with the gravitational nudges from giant molecular clouds and spiral arms, would have slowly but surely pulled the cluster apart. The once tightly bound family of stars would have evaporated, its members drifting apart to mingle with the billions of other stars in the galactic disk, becoming indistinguishable from the stellar background. Our Sun's siblings are now scattered across the Milky Way, a diaspora of stars that likely number in the thousands, all sharing a common origin, but now lost to one another. Finding them is one of astronomy's greatest detective stories. How do you identify a few hundred or thousand stars out of the hundreds of billions in our galaxy, all of which originated from the same long-vanished cluster? Astronomers are hunting for them using a technique often called chemical tagging. The idea is that all stars born from the same giant molecular cloud will share a unique chemical fingerprint, a specific ratio of elements like iron, oxygen, and silicon that acts like a shared DNA. This signature would be subtly different from stars born in other clouds elsewhere in the galaxy. With powerful telescopes and spectrographs, scientists can measure the composition of thousands of sun-like stars with incredible precision, looking for those that match the sun's unique elemental pattern. This is a monumental task, akin to finding a few specific grains of sand on a vast beach, but projects like the Gaia Space Observatory are making it possible. Gaia is precisely measuring the positions, distances, and motions of over 1 billion stars. By combining this detailed map of stellar motions with the chemical fingerprints from ground-based telescopes, astronomers can look for stars that not only share the sun's chemistry, but also have orbits that, when rewound mathematically, intersect with the sun's path billions of years ago. A few promising candidates have already been proposed, stars whose composition and dynamics suggest they could be long-lost relatives. While a definitive, large family group has yet to be confirmed, the hunt itself validates the profound idea that our seemingly solitary sun is, in fact, a refugee from a much larger and more dynamic stellar family, its ancient birthplace now dissolved into the great expanse of the galaxy. This grand narrative of stellar interactions and galactic mergers now brings us to a subtle but relentless force that governs the very orbits of these clusters, a slow-motion gravitational drag sealing the fate of many. Imagine a globular cluster, a magnificent city of stars, orbiting the center of our Milky Way. It's not on a static, eternal path. Instead, it is gradually sinking, losing altitude in the galaxy's gravitational well, spiraling ever inward toward the brilliant, crowded core. This process is driven by a fundamental physical mechanism known as dynamical friction, and it acts as a cosmic countdown timer for the cluster's existence. The underlying principle is both elegant and profound. As a massive object like a globular cluster moves through the galaxy's halo, it doesn't travel through empty space, but through a diffused sea of dark matter, isolated stars, and remnants. The cluster's immense gravity slightly perturbs this background population as it passes. It creates a subtle, trailing gravitational wake, a region of slightly enhanced density behind it. This wake, in turn, exerts its own gravitational pull back on the cluster. Crucially, this pull acts against the cluster's direction of motion. It's analogous to moving through water. Your motion is resisted by the very medium you're displacing. For the cluster, this resistance is a continuous, gentle brake, steadily sapping its orbital energy. This loss of energy doesn't cause it to slow down in a straightforward way. Instead, it causes the cluster's orbit to decay. The immense spiral path gradually tightens, drawing the entire stellar city closer and closer to the galactic center with each passing million-year cycle. The ultimate consequence of this orbital decay is nothing short of the complete destruction of the cluster. As its orbit tightens and it begins making closer and closer passes to the galactic core, it encounters vastly stronger tidal forces. Remember those tidal tails we discussed earlier, formed by the gentle stretching of the galaxy's pull on a distant orbit? For a cluster suffering orbital decay, this process is dramatically amplified. During each perilously close periapsis, the point of closest approach to the galactic center, the difference in gravitational pull between the near and far sides of the cluster becomes immense. This doesn't just peel away a few outer stars. It can violently strip away vast swaths of the cluster's population in a single pass. The cluster is essentially being shredded, its stars ripped from its gravitational grasp and flung into chaotic orbits around the galactic center. Over a series of such close encounters, the cluster is completely dismantled. Its identity as a distinct, bound system is erased. The stars that once belonged to a cohesive community become just more members of the galaxy's bustling central bulge, or the diffuse stellar halo. This process provides a direct and sobering explanation for the missing cluster problem we encountered at the very beginning of our journey. the hundreds of globular clusters we see today are not the entirety of what once existed. They are merely the hardy survivors, the ones that formed on stable, wide orbits far from the galactic center, where dynamical friction acts incredibly slowly and tidal destruction is less of a threat. The countless others that formed on unfortunate, plunging orbits have long since been consumed, their stars assimilated into the larger galaxy. Their absence is a silent testament to this relentless orbital decay. This relentless infall of clusters is not just a destructive process, it is also a primary mechanism of galactic construction. Every globular cluster that spirals inward and is torn apart contributes its stellar material to the galactic bulge, the dense central congregation of stars that forms the heart of our Milky Way. Think of it as a form of cosmic delivery service. These clusters, some of the oldest structures in the universe, are literally raining down onto the galactic center, depositing their ancient stars and any stellar black holes or neutron stars they contain. This contributes significantly to the buildup and growth of the bulge itself, but the influence may extend even deeper to the very nucleus of the galaxy. Many astronomers theorize that the supermassive black hole lurking at the exact center of the Milky Way, known as Sagittarius A, could have grown in part by feasting on these in spiraling clusters. As a cluster's orbit decays and it ventures into the extreme central region, its stars can be scattered directly into accretion orbits around the black hole. Even if the stars themselves aren't consumed, the process of dynamical friction can deliver the cluster's own central intermediate mass black hole, if it has one, into the vicinity of the supermassive black hole. The two black holes would then form a binary pair, and as they themselves spiral inward through gravitational wave emission, the smaller black hole would eventually merge with the giant, providing a substantial meal that adds to its mass. This paints a picture where the majestic globular clusters we admire are not merely decorative features of the galaxy. They are active participants in its architectural evolution, their slow-motion death spirals helping to build the very central engine that governs the galaxy's dynamics. The survival of any given cluster, therefore, becomes a high-stakes cosmic drama dictated by its initial conditions. A cluster's fate is largely sealed at its birth by the specific orbit it acquires. Those born with a large amount of kinetic energy placed on wide, circular orbits far from the galactic center experience minimal dynamical friction. For them, the journey inward is so slow that the age of the universe itself may not be long enough for them to be destroyed. They are the privileged long-term residents of the galactic halo. In contrast, clusters born on elliptical or eccentric orbits that swing them repeatedly close to the dense central regions are living on borrowed time. Each close pass not only strips stars, but also increases the effectiveness of dynamical friction, hastening their demise. This explains the observed distribution of clusters in galaxies like our own. We find the majority of them in the outer halo, a direct reflection of this ruthless selection process. The clusters we can easily observe and study are the fortunate ones, the winners of a gravitational lottery that condemned their siblings to an early demise. Their continued existence allows us to glimpse the ancient universe, but their missing counterparts remind us that the cosmos is in a constant state of flux, where even the most magnificent and durable-looking structures are subject to the slow, inexorable laws of gravity playing out across billions of years. And just as we use the rhythmic pulses of variable stars to measure our local galactic neighborhood, astronomers have uncovered an even grander cosmic yardstick, one that uses the collective glow of these entire stellar cities to map the vast distances between galaxies themselves. This is the Globular Cluster Luminosity Function, or GCLF, and it stands as one of the most unexpectedly reliable tools in the extragalactic astronomer's toolkit. The principle behind it is beautifully simple. When you look at a large galaxy, like our neighboring Andromeda, you don't just see the galaxy's smooth glow. You can also pick out its population of globular clusters, each one a tiny, distant point of light. If you were to count these clusters and plot a graph of their brightness, their luminosity, you would find that they don't follow a random distribution. Instead, they form a distinctive bell-shaped curve. The crucial discovery was that the peak of this bell curve, the most common luminosity for a globular cluster in a large galaxy, is remarkably consistent. It's as if nature has a preferred wattage for these ancient stellar systems. This means that by simply finding that peak brightness in a distant galaxy's globular cluster population, astronomers can determine its distance with surprising accuracy. They know how bright these clusters should be intrinsically, so by measuring how dim they appear, they can calculate exactly how far away the host galaxy is. This transforms entire populations of globular clusters into a single, powerful standard candle, allowing us to measure cosmic distances on an immense scale. However, the true power of this tool lies in its subtlety and the nuances that astronomers have had to unravel. The GCLF isn't a perfectly rigid standard. Its shape and peak can depend delicately on the type of galaxy it belongs to. In giant elliptical galaxies, which are often the result of dramatic galactic mergers, the globular cluster population is typically vast and rich. The luminosity function in these galaxies tends to be broader and can sometimes even show a distinct double peak. This bimodality is a fossil record of the galaxy's violent past. One peak might represent the native population of clusters that formed with the galaxy itself, while the second, often bluer peak, corresponds to clusters that were stripped away from smaller galaxies during collisions and cannibalism. In contrast, spiral galaxies like our own Milky Way usually host a more homogeneous collection of clusters, resulting in a cleaner, single-peaked luminosity function. Understanding these variations is not a weakness of the method, but its greatest strength. It forces astronomers to become cosmic demographers, studying the entire population of clusters to understand the history of their host galaxy. By analyzing the width of the luminosity function, for instance, they can infer the rate of dynamical destruction that has occurred over billions of years. A broader spread suggests a more violent dynamical history, where many lower mass clusters have been destroyed, leaving a wider range of surviving luminosities. This makes the GCLF more than just a ruler. It is a historical document, its shape encoding billions of years of galactic evolution, from peaceful formation to cataclysmic mergers. The application of this technique has been nothing short of revolutionary, particularly in the study of the local universe. Before we had ultra-precise methods like those from the Hubble Space Telescope's Key project, the GCLF was one of the primary tools for pinning down the distance to our largest neighbor, the Andromeda Galaxy. By meticulously measuring the apparent brightness of hundreds of its globular clusters and finding the peak of their luminosity function, astronomers could confidently place Andromeda at a distance of around 2.5 million light-years, cementing its status as a separate island universe far beyond our own Milky Way. This method has since been applied to galaxies throughout our local group and beyond, providing crucial independent checks on other distance measurement techniques. Its reliability stems from the law of large numbers. While any single globular cluster might be unusually bright or faint, the average properties of a large population are incredibly stable. This robustness makes the GCLF an indispensable part of the cosmic distance ladder, bridging the gap between the relatively nearby measurements we get from variable stars and the far more distant indicators used for cosmology. In an era of increasingly precise astronomy, this elegant use of entire populations of ancient star clusters continues to provide a fundamental anchor for our map of the cosmos. proving that sometimes the most reliable markers are not individual stars, but the collective light of millions of them, shining in unison across the vast intergalactic void. Yet even as we use these clusters to map the grandest cosmic scales, their own incredible density offers a way to probe the very fabric of spacetime, turning them into colossal natural telescopes. This brings us to the fascinating, though still largely theoretical, potential of gravitational lensing within their borders. Picture a globular cluster not just as a collection of stars, but as a massive, intricate lens made of gravity itself. According to Einstein's theory of general relativity, a massive object warps the space around it, and light from a distant background object like a far-off galaxy or a quasar will follow this curved path as it passes by. The result is that the light is bent and distorted, often magnified or even split into multiple images. While we typically associate this dramatic effect with entire galaxies or massive galaxy clusters, the sheer density of stars in a globular cluster means it, too, could produce its own, more subtle version of this phenomenon. Within a cluster, the primary form of lensing we might detect is known as microlensing. Instead of the entire cluster acting as a single, coarse lens, its individual stars can each create their own tiny, temporary lensing event. Here's how it works. Imagine a faint, distant star located precisely behind the cluster from our viewpoint on Earth. As the cluster moves through space, one of its numerous foreground stars will, by chance, pass directly in front of this distant background star. The gravity of the foreground star acts as a miniature lens, briefly bending and focusing the light of the background star. From our perspective, the background star appears to momentarily brighten, sometimes by a factor of hundreds, before fading back to its normal luminosity as the alignment passes. This event is transient, typically lasting only hours or days, but it provides a direct and incredibly powerful measurement of the mass of the foreground star doing the lensing, independent of its light. This is the true power of microlensing. It can weigh objects that emit little or no light at all. This capability opens up a revolutionary way to take a complete census of a globular cluster's hidden population. We now know these clusters are teeming with dark, massive objects, stellar mass black holes, neutron stars, white dwarfs, and even faint, low-mass brown dwarfs that are nearly impossible to see directly. A microlensing survey, which would involve meticulously monitoring the light of millions of background stars for these telltale flashes, could detect these invisible residents purely through their gravitational influence. We could finally get a statistically sound count of the black hole population, confirming or refuting theories about how many remain trapped in the core. We could uncover a vast sea of white dwarfs, the faint remnants of the cluster's earliest stars, directly measuring their masses and testing our models of stellar evolution. We might even discover a population of free floating planets that were ejected from their parent stars during dynamical encounters, objects that would otherwise be completely invisible to us. Each microlensing event is like a momentary spotlight, illuminating a single dark object and revealing its mass, offering a way to build a full inventory of the cluster's dark matter in the form of these compact stellar remnants. Beyond simply counting dark objects, microlensing offers a unique and direct method to map the cluster's total gravitational potential. When you observe thousands of these fleeting events scattered across the face of the cluster, you get more than just individual masses. You get a detailed picture of how all the mass, both visible and dark, is distributed. The rate and characteristics of microlensing events depend on the density of the lensing objects. If a cluster possesses a significant halo of the elusive particle-based dark matter, something still hotly debated, it would subtly increase the number of microlensing events we would expect to see, particularly in the cluster's outer halo, where normal stars are sparse. By comparing the observed lensing map to the distribution of light from visible stars, astronomers could, for the first time, directly detect and measure this dark matter component, settling one of the most profound questions about the fundamental nature of these ancient systems. They could determine if the mysterious dark matter candidates we've discussed are real, or if the clusters are truly baryon-dominated as traditionally believed. Even the tiny deflections of light caused by the combined gravity of all the stars, a subtle effect known as weak lensing, could be used to weigh the entire cluster with unparalleled precision. This technique would measure how the images of countless background galaxies are coherently and minutely distorted as their light passes through the cluster's gravitational field, providing a direct measure of its total mass. While observing these subtle effects in a globular cluster remains an immense technical challenge, future observatories with razor-sharp vision could turn this idea into reality. The ability to use gravity itself to weigh and dissect these stellar cities would mark a new era in our understanding, transforming them from distant points of light into fully mapped gravitational structures, their every hidden component revealed by the way they bend the very path of light traveling from the distant universe. And so we've traveled through a cosmic gallery of the bizarre and the beautiful, from stars older than the universe itself to stellar phoenixes rising from collisions, from hidden black holes to ghostly tidal streams. We've witnessed the chemical drama of multiple generations, seen the violent cores on the brink of collapse, and pondered the possibility that our own sun has thousands of long-lost siblings scattered across the galaxy. What began as faint, fuzzy smudges of light in our telescopes have been utterly transformed. They are not the simple, serene relics we once imagined. Instead, they are vibrant, dynamic, and often chaotic ecosystems. They are chemical factories, stellar demolition derbies, gravitational wave engines, and cosmic time capsules all rolled into one. Each discovery, from the blue stragglers and the second parameter problem to the potential cradles of fast radio bursts, has chipped away at our simple models, forcing a profound and humbling realization. These ancient star clusters are not just ornaments of the cosmos. They are active, living laboratories where the fundamental laws of physics are stretched to their absolute limits. They challenge our understanding of how stars are born, live, and die. They rewrite the story of how galaxies are built through cannibalism and merger, and they provide our most direct window into the violent, formative years of the universe itself. They are the ultimate teachers, proving that the universe's capacity for wonder and mystery is truly endless. Now, we turn the conversation over to you. After this whirlwind tour of 30 strange discoveries, which one shattered your cosmic perspective the most? Was it the concept of a star seemingly older than everything, the idea of black holes endlessly dancing in the core, or the thought that our solar system might have been born in a brilliant, violent cluster? Let us know in the comments below what discovery you found the most mind-boggling. And if you're eager to continue unraveling the universe's greatest puzzles with us, make sure to subscribe and hit the notification bell so you never miss another deep dive